Good morning to all of you. Today is our second lecture on highway geometric design, and we had covered the basic things about how highway planning starts and how we do the project, and the basic design of that we discussed yesterday, which was stopping side distance, overtaking side distance, and that is what we actually the basic or the stepping stone for the geometric design. And we'll be further discussing few other components which will be helping us to put together all the design elements and design the overall alignment. So today we'll be more focusing on the horizontal alignment. So we are starting with the horizontal alignment design. So the main horizontal alignment, whenever we are doing the design, there are basic elements which we are going to target or we will be designing. And these elements of the horizontal alignment are the cross-sectional elements, horizontal radius of curve, horizontal transition curve, which is actually connecting the circular curve or the radius with the tangent section. So if you look into a horizontal alignment, basically what is going to happen, you will have a tangent section which is the straight portion of the roadway, and there is a curve section. And if you recall yesterday's lecture, our alignment is actually a three-dimensional space. However, whenever we are representing into two different two-dimensional space. One is in XY plane, which is your horizontal alignment, which is you are looking under plan view, and the other is on XZ plane, which is your vertical profile or alignment, and which you are looking at the plan or profile, the profile view. So when you are looking into this horizontal alignment, there are various components, and the main component are like the tangent section, which is connected with the curve section. In between the curve and the tangent, there is a transition curve. So this is what is about the horizontal transition curve. Then the other component is the super elevation. And apart from super elevation in the horizontal curve, we do need to provide extra widening. Why we do need to provide the extra widening, how we do provide the extra widening, we'll be discussing as we progress. We also need to look into the setback distance and the other element which is part of the vertical profile is the vertical curve. So these are the overall elements of a highway alignment, and there is also a gradient. So today we will be looking into the various elements, how we look into these factors and how we do design each of these elements. Okay, so let's move on to the next slide, and where we will be looking at the different cross-sectional elements. So in the earlier slide you saw that we said about the cross-sectional elements. So what are these cross-sectional elements? The cross-sectional elements, one is the and their characteristic, one is the pavement surface itself, that the top surface, whatever you see, is actually a part of the cross-sectional elements. And how does it matter? The top surface provides friction, and the friction helps in skid resistance. So definitely when you are designing, we need to know what is the skid resistance, whether our vehicles are going to slip off or whether it's going to skid or not. So we need to know that. Even though it is not directly part of the geometric design, but somehow it is incorporated in the geometric design, and as we progress, you will see why and how we need this. The other part is the pavement unevenness. So the pavement unevenness, if the pavement is too rough, the riding quality is not going to be good, and it may lead to unsafe movement of the vehicle. And the third thing about the pavement surface is the light reflection characteristic. So again, we will be discussing this thing, light reflecting characteristic of the surface, why we need it, how it helps. The other cross-sectional elements are the cross slope or the camber, which when you travel on the roadway, you will see that the road is inclined in both sides from the center line. Why we provide, how much inclination we should be providing, the slope that we will be discussing. Width of the pavement, this is a very important thing, and one of the important part deciding factor is traffic. So if you consider a roadway where the traffic is quite high, definitely you need more lanes, and that is what we say, like, oh, the traffic has gone up and it's so congested. So how to uncongest the road? Add lanes, make it widen. So that is what the pavement width or the pavement width of pavement or carriageway means. And then apart from roadway, you will see on the or the pavement surface on which you are traveling, you will see there are certain other reserved land parcel on the both side or empty land parcel for various purposes. Somewhere there is a footpath and there are signs, there are longitudinal drains. So all this included in the road margin, and so the extra land width on both sides of the roadway, whatever we have, is road margin. I'll show you through a picture what is this road margin, where we need it, and what can be accommodated in that part. Now, sometimes your road may need to be elevated from the basic ground profile. So, if it is elevated, that means you need to provide a side slope of 2:1 or depending on the soil characteristic, and which means whatever the width of the roadway on the top is not going to match with the bottom or the base. So it's going to be different. So the width of roadway or formation is quite important for this, to know how much land we need to construct the roadway and how it is going to affect the alignment. And overall, including everything, road margin, the formation width and everything, we need to know what is the right of way we have, or the land which we have can be used for our construction. So these are the various cross-section elements, and if we move on to the next part, which is the pavement surface, which we'll be discussing now in detail, the first thing we said about, we need to know about the friction. If you recall, when we are discussed about stopping side distance, we assumed the pavement friction to be 0.35 to 0.4. So it depends on the pavement quality or the characteristic on the top, what it is, so that we can achieve at least 0.35 to 0.4 friction factor, or the coefficient of friction. Now, if your friction is too high, that means your it is going to affect the operating speed and the fuel consumption. If it is too low, it is not safe. So if it is low or some problem is there, what are the indicators that we don't have enough friction? One is the skid. So the skid is actually when the vehicle skids in a direction of the movement, and it can be defined more as when the wheels are rotating less than the distance traveled by the vehicle. So that is when the vehicle is skidding. The other component is slip. The slip is when actually the wheels rotate more than the distance traveled by the vehicle. So there are two different conditions, and when does this thing occur? Skid generally occurs like when the vehicle is want to decelerate and the brake is applied, so you may see there is a skid. And the slip, when the vehicle is trying to accelerate, and if there is not enough friction, so the wheel may rotate freely, and at that time the slip may occur. Now, as I told you, there are certain recommended values for the friction. So now, if you see the vehicle is moving in the longitudinal direction, the vehicle also needs certain amount of friction in the lateral direction, because we need the vehicle needs to be stable in the lateral direction as well. So what is going to happen in the lateral? Like if it is negotiating a curve, definitely there is a centrifugal force. That centrifugal force is going to try to pull the vehicle away from the road. So definitely you need some lateral friction. As well as the vehicle, as it is traveling even on the tangent section, it is deviating a little bit on the left or right, and in that situation it does need some lateral friction. So as per IRC recommendation, the longitudinal friction coefficient is about 0.35 to 0.4, and the lateral friction coefficient is about 0.15. So the point to be noted here, the lateral, it's the same pavement, same tire, but the lateral friction coefficient is quite low. The reason behind this is that we need the vehicle to be laterally stable, because if the vehicle is not stable and if it is actually sliding in the lateral direction, it is very difficult to control the vehicle, and we need absolute safety in that direction. Because in that case, the vehicle can be thrown out off the road, and it can be actually get into accident. Whereas the longitudinal, there is little bit better control because of the steering and other things, and that's why we can get this friction. And the other thing you have to notice here that the longitudinal friction, the IRC provide a range. Now, how to use this? This is up to the designer, considering the weather condition and considering other factors. They need to be in the conservative side, or they can be on the higher side. So yesterday there were a few discussions where someone was asking about how should we improve the weather condition. So here is an opportunity to consider the weather condition by considering lower friction coefficient. Now the other characteristic of pavement surface are the pavement unevenness. So in the pavement unevenness, basically you are monitoring how uneven the pavement is. If your pavement is too uneven, then your ride quality is not going to be good, and it is going to affect the operating cost of the vehicle, and as well as comfort and safety. Then how do we measure this one? So the way we measure it is by bump integrator. It is a type of equipment which is actually attached to a vehicle, and once the vehicle travels at certain speed, the amount of bump it occurs, that is noted, and integrate all the bump values and then come up with a combined index. So the combined index is generally represented as in the unit of centimeter per kilometer. In IRC, sometimes they indicate it as millimeter per kilometer. So it's just a factor of that. And the value which is recommended for a high-speed highways is 150 centimeter per kilometer. For satisfactory up to a speed of 100 kmph is about 250 centimeter per kilometer, and very uncomfortable speed of 50 kmph, it can be 350 centimeter per kilometer. So this is how you look into the quality of the pavement, the evenness of that. Okay, so now I'll move on to the next slide, and before I move there, there are two questions which I'll be addressing. One is that which is the more complicated in between skid and slip. So if you look into the situation when it is happening, skid is happening when you are applying brake and the vehicle you are trying to stop and it will take longer distance. Whereas slip is happening when you are trying to accelerate, or when you are when the vehicle is starting from the stand or stop position. So in this case, again you are trying to accelerate and the wheels started slipping. So if you look into this, understand this situation, probably the skid is most of the time it's quite dangerous, because you want to stop at a certain distance and it didn't stop, means there is the chance that vehicle can get into an accident. Whereas slip, yes, it can lead to the accident, but it is actually you are trying to go at a higher speed. So if you don't attain the higher speed, you are still at a lower speed, and if you can manage it, probably you can control. The other question I got was, what will be the coefficient if brake efficiency is 70%? So whatever the coefficient you assume for that, you multiply with that 70% efficiency. So if it is 0.35 you have assumed for the friction coefficient, multiply it with 0.7 and use it for calculating the stopping side distance. So but the coefficient, as such, the friction coefficient will remain same, because brake is a different entity and the friction between the pavement surface and the tire is a different entity. So we are looking from two different aspects, and once we combine these two, that is going to reflect in your stopping side distance. So now I'll move on to the next slide. And the other pavement surface characteristics which are quite interesting, or which we need to look into, was the light reflecting characteristic, and because it is going to affect the visibility. Now if there is a glare from the headlight and which reflect on the pavement surface when it is wet, or then definitely it is going to affect the safety of the vehicle or the driver who see this glare. So if we want to consider a pavement surface where there is a minimum glare during these conditions, and if you look into the night condition, then in the night condition we'd like to see a pavement which is of light color, and so that it reflects more light. So a concrete pavement which is of light color is good for the night time, whereas it may not be good in the daytime because it may create a lot of glare. Whereas the bituminous pavement which is dark may not be good in the night time. So we need to have a quite balance, and this is one of the reason actually we also provide this white pavement marking, which is helpful in the night time. And nowadays this pavement, these paints are comes with small glass beads to make it retroreflective, so that when the light falls on that and it reflects back and gives you an idea where the pavement edge is, where what is the lane and so forth, and to make the road safe. And then now I'll move to the next slide. Before I move, I got another question. It's about if bump integrator is used to measure unevenness, then for roughness index, which instrument is used? The roughness index is a parameter which is obtained through this measurement of unevenness. So bump integrator is actually measuring unevenness, and it is giving you the index value, the roughness index value. So it is the same equipment which is giving you the roughness index. So now moving on to the next part, another cross-section element, which is the cross slope or camber. As I told you, when you travel on the road, you will see that the road is sloped on left and right in a straight tangent section. This is not a super elevation or the banking which we need to provide, but this is actually cross slope. And why do we provide this? Because we don't want water to be stagnant on the road surface. We want the water to drain off. And how the water can drain off easily? If we can provide a slope on either side, which is going on the either side of the road. And this is the shortest distance the water can travel and get off the road surface. And this is why we provide the camber. And if you look into the camber, generally it is referred or designated as 1 in n, that is 1 vertical versus n horizontal, or by percentage, x percentage of slope. The thing is that if you provide less camber, or if there is no camber, then water may accumulate on the surface and it can damage the pavement, as well as it is not safe when the vehicles are driven through this roadway. So it may create hydroplaning. If you provide too much of camber, it can also cause discomfort to the driver. So if it is too much of camber, you will see that drivers are actually driving at the middle of the road, not right on the side of the road according to the lane, because if they will be actually tilted when they are actually on the side of the road. So now there are various kind of camber, and the choice depends on the type of pavement surface and the amount of rainfall. And how this is going to help the pavement surface and amount of rainfall will come in the next slide. Here if you see that the cement concrete pavement, which is quite impervious compared to bituminous pavement, the water can easily run off or drain off, and it is not going to penetrate the pavement and damage it to the extent what it can do to the bituminous pavement. So in this case, the cement concrete pavement, we provide a milder cross slope or camber, which is from 2% to 1.7%. Now when we provide 2%, when the rain is heavy, the rainfall is heavy. And when we provide 1.7%, it is when the rainfall is low. So this is how we are considering the climate, and the material and the pavement type we are considering the other way. Like when we are providing the thin bituminous surface, so basically we can, the bituminous surface can get damaged if there is some slight of water stagnant there. So we want the water not to be stagnant, and it needs the water to run off easily. So this is why you will see that the camber here, the slope is quite high, 2.5% to 2%. Now, if you look into the 2.5%, it is where the heavy rains are, and 2% is where it is low. For waterbound, again, we don't have coating like bituminous coating in these cases. So here, the bituminous, in this case, you will see that the camber percentage is even more, because we don't want the water to percolate and we want the water to just go off easily. And in case of earthen, it is the highest. So it's 4% and 3%. Now this is about the carriageway where, or the travel lanes where the vehicles are traveling. Then beyond this, there are shoulders on either side of the roadway. So the shoulders are generally made of inferior material compared to the main carriageway. So what we do, we need to provide more camber on the shoulder compared to the main carriageway, and also you want the water to be off of the roadway as soon as possible, because even on the shoulder, because shoulder is going to be used in the emergency cases. So what we say, the cross slope of shoulder should be 0.5% steeper than adjoining pavement surface to the maximum of 3%. So the maximum of 3% when you are saying that, we are assuming the shoulder is at least of waterbound macadam type of or gravel type of that kind of material. If it is earthen, means everything is earthen, so definitely you have to provide 4% to 3% all throughout, even on the shoulder. As I told you that the camber is also going to create discomfort if you put too much of camber. And so expressway, whenever you want constructing an expressway and which is of higher speed, and that is why we are limiting the expressway camber to be 2.5% of the carriageway, and also the same thing we are providing on the paved shoulder and S-strip. Why we are providing the same on the expressway? That is because if you look into the expressway, vehicles are expected to travel at a very high speed, and shoulders are going to be used when there is an emergency stop. And when there is an emergency means the vehicle traveling at 100 or kmph or 80 kmph, they will be gradually shunted to the shoulder and then travel and safely stop. So in the shoulder also, sometimes they can travel at considerably high speed. So there we don't want a steeper cross flow. So this is why we are providing about 2.5% cross flow. Okay, so now before I move to the next slide, I got another question. So the question is, camber is also required for porous concrete pavement. The porous concrete pavement, generally the porous concrete pavement is not used on the travel path. So far what I have seen or what I have known is that the porous concrete pavement, which is generally used for the sidewalk, and that is a common practice in US. I have noticed that they are using it in the sidewalk. And in the porous pavement, so there it can be flat, and on the travel path, if it is not porous, definitely you have to make sure that it has some camber. Now we'll move to the next slide, where you'll see the different type of cross slope or the camber. So basically you will see the three different type of shapes. One is the parabolic, which is on the top left side. The other is the straight line camber, which is on the right side top, and then the combination of those two, which is you see in the bottom. Now if the pavement is made of bituminous, you will see mostly it's of parabolic nature, because the bituminous material, when it is laid, and can be easily shaped to this. Whereas when it is concrete, rather than parabolic, it is better to, or it is easier to shape it or in a straight line camber. So the concrete pavements you will see more in a straight line camber, and if the concrete pavement in the center, if you cannot make it like the edge, like what you see, or basically it will become little bit parabolic. So you can see a combination of straight and parabolic camber, which is shown in the bottom. So the for the concrete pavement, you will see the combination or the straight line camber, whereas for the bituminous pavement, you will see the parabolic camber. So now the other component of this is the pavement width or the carriageway width. How do we decide this? It is coming from the vehicle characteristics. Yesterday, if you recall that we were taking, we need to understand our design vehicle, and the vehicle which are going to use our facility. So vehicle in general, the width is considered, particularly the bigger size truck, and standard width is almost 2.5 meter. So whenever a vehicle is flying which has a width of 2.5 meter, you need some clearance on either side. And so for a single lane, the clearance considered on both sides is 0.625 meter or 625 millimeter. Now, if we add all these three dimensions, you will get the pavement width of 3.75 meter, and this is the pavement width for the single lane. When it comes to the two lane, means you are expecting that there are two vehicles which is going to go next to each other. This vehicle width is again 2.5 meter for each, and when it is 2.5 meter on each side, then you need some clearance between the two vehicles, that is 1 meter, which is provided, and either side, edge side, basically up to 0.5 meter is considered. So if you add up all these three, this is going to come up as a 7 meter, and that is the width we consider. And so multi-lane, basically we consider the multiplication of 3.5 meter lane, whereas if it is single lane, we provide little bit more and it comes to be 3.75 meter. So before I move on to the next slide, I can see there is one question which is related to the color of pavement. So light color are preferable during rainy season, but they glare in sunlight in general. Which color should be preferred? The preferred, it depends, as I told you, it depends on the condition. So night time you will be preferring light color, daytime you will be preferring dark color, but we cannot provide both. We have to have some, I mean, if you are using the bituminous, it's going to be dark color. If you are using concrete, then it is going to be light color. So we have to see how through other arrangements how we can make it more visible. So for that is why we provide this lane marking. That is why we provide the other features like cat's eye and all those details, so that it becomes more visible at different conditions. So the preference is one thing, but what we get is the different thing, and we have to consider how best we can utilize that. So now let's look into the pavement width, what IRC recommends. So IRC recommends for the single lane, as I told you, 3.75 meter, two lanes without raised curve is 7 meters. So now if there is a raised curve, means the vehicle cannot go on the left or right. In that case, it is 7.5 meter. So which is a multiplication of 3.75 meter. And if it is intermediate carriageway, as I told you yesterday, that there are certain sections of the roadway where there could be the width, we are not going to provide either single lane or double lane. In this case, we are providing 5.5 meter, and we are expecting that the traffic volume is quite low, and there is once in a while you will see that there are vehicles coming from the opposite direction and they need to slow down and pass. But nowadays, most of the intermediate lanes are being converted to 2 lane at least. And in the multi-lane pavement, as I told you, it will be the multiplication of 3.5 meter per lane. Now, these are the, when you are providing 3.5 meter or 3.75 meter, these are for a higher speed road. So at the end where you have enough land width. Now, if you are in a local street where the speed is quite low and you don't have a lot of right of way, in this case, basically you can have a pavement width of up to 3 meters. So you will see that there is an exemption in case of local street or residential area. This width can be considered as 3 meter. Urban road without raised curve is considered as 3.5 meter, and expressway in mountainous terrain is also considered as 3.5 meter, even though these are single lane in case wherever there is single lane. So these are the pavement width. Once we know the pavement width, let's look into the margins. So once we are looking about the margin, as I told you, we have a carriageway through which the vehicles are traveling. Apart from on the either side of the carriageway, there is a shoulder. This is for the safety. When in emergency, the vehicle can stop there. So altogether, the shoulder and the carriageway is called the roadway width, because shoulder can be used as a roadway. Beyond roadway, you are going to provide, if it is elevated highway in the sense like there is an embankment, you need to have a side slope and all those thing that will, and also you need the longitudinal drain. So these things are provided in the margin, and also you need to provide certain signs at certain location. These are again you need to be accommodated in the margin, and altogether whatever width you need to accommodate everything is going to take up or is actually part of your right of way. So your right of way is actually more than your carriageway. And now we'll look into what are the different roadway width or the right of way width considered recommended by IRC. So IRC recommend for the single lane national highway, at least in a plain and rolling terrain, it should be 12 meters. So you can imagine that a carriageway for single lane is only 3.75, whereas for the single lane national highway we are considering right of way of 12 meters. Why? Because in future it is definitely going to be converted into 2 lane. So this is why you will see for the 2 lane also it is the same width we are considering, 12 meters. So it has been adjusted for the 12 for that 2 lane. Now when you are going into the mountainous or the steep terrain, you don't have enough land there. So there you need to squeeze everything in a shorter cross section. That is why for the single lane you see that the right of way expected is 6.25 meter, and for the 2 lane is 8.8 meter. And by the way, these are the recommendation. It doesn't mean that the right of way has to be 6.25 meter. It is the minimum. The right of way can go more than that. If it is available, it's better to provide 12 meter even in the hilly terrain and mountainous terrain. For the major district road where you don't have lot of facility or the things on the side of the road, it can be little bit on the lower side. That is why the right of way is also on the lower side. It's 9 meter for single lane, and the single lane is expected to be converted into 2 lanes. So that is why it remains 9 meter. Other district road, again, the same thing it applies. For the single lane it is 7.5 meter, but when it comes to 2 lane it becomes 9 meter. And then the village road, it's expected the village road is single lane. At most it will have enough shoulder for the vehicles to cross each other, and you won't see vehicles of 2.5 meter width. That means a bigger truck or those things. So you will see a small car or 2-wheelers. So that is why it can go with just 7.5 meter and a single lane. So this is about the overall right of way requirement. Sorry, this was about the roadway width. So right of way requirement will come up beyond this. So roadway width, if you go back to this particular thing, it includes your shoulder and the carriageway. So all this together is the roadway width which you are providing, the plain surface on top of after embankment and everything. Now, if you go back to the apart from that, you need to provide the margin. So once you include the margin, then you are going to get the right of way. So in this right of way, basically an agency needs to acquire this land for construction. And when they are going to use this one, this depends on the kind of embankment you need at certain sections. So if you have a high embankment, means your cross slope is going to be, or the foundation is going to be spread at a wider area or wider cross section, and then you need more right of way. And it also needs the side slope. So if you have a stable slope in 1:2 slope, then you need certain width, and if it requires 1:3, then the width is going to increase, and so forth. The fourth thing is that the type and size of drainage system. So the type and size of drainage system means if you require bigger size drainage system which requires more water to flow, then definitely you need wider right of way, because that drainage is considered in the margin, and the margin along with the roadway width is going to give you the right of way. And the other part is the side distance. So while you are considering the side distance on a horizontal curve, you will see as we progress. So coming to the right of way from IRC, the recommendations are quite high. So expressway, you will see the right of way in open areas in normally it is 90 meter, and in mountainous and steep terrain it can be 60 and 30. So 30 is like split level. Split level means your one direction is in a different level and the other direction movement carriageway is in a different level. So when you split it, so each side is considered a separate alignment. Technically, we consider it as a separate alignment. When we consider it as a separate alignment, we consider like for each alignment we need 30 meter right of way. So 30 plus 30, it will add up to 60 meter. So national and state highway, the requirement is less, and for the national and state highway there is a range as well. So preferably, normally it is going to be 45 meter for national and state highway, but occasionally at some location there could be a pinch point where it can reduce to 30 meter and it can go as high as 60 meters. So considering the future development and other things, conversion of a state highway to national highway or national highway to expressway, it's better to have more right of way, and also for this side distance at a curve, sometimes we may need a higher right of way. So this is the overall table for different category of road. What is the different right of way needed? Now let's move on to the some interesting design elements. So one of the design elements we discussed in the last class or yesterday was about the stopping side distance. Now the stopping side distance, all this we may consider it in the tangent or on a curve. So in the curve, another thing is actually happening. There is a centrifugal force which is going to pull the vehicle out of the road on the outer side of the curve. And if you look into the centrifugal force, basically this is the centrifugal force which is going to act on it. So W is the weight of the vehicle weight, and D is the speed, and by G times R is the radius. So if we know this is what the centrifugal force is going to be, what this force is going to do, it is going to either make the vehicle overturn or it is going to make the vehicle skid in a lateral direction. And how we should balance it will be coming to the next slide. Before I go to the next slide, now there are questions about what should be the minimum width of median and shoulder in national highway. So shoulder, I think the national highway, they say about 1.5 or 2 meter, something like that. So I'm not exactly sure. You can look into the IRC code and that value is there. And about the median, generally they prefer if it is about 10 meter or depending on the future improvement. So 10 meter and minimum they can go up to 2.5 meter, something like that value. So these values are not written on stone, or there are certain guidelines, and what is the purpose of this, we need to look into that. And as I told you, the shoulder is just to accommodate a vehicle, stopped vehicle during emergency. So you can have about 2 meter, maximum 2.5 meter, where the vehicle can just comfortably park in the shoulder. So it can vary from 1.5 to 2.5 meter, and that should be good enough. So that is for the width. Now I got another question: is there a separate specification for right of way in urban areas where space is limited? So if you see the table right of way, I think it also says built up area. So built up area is more like an urban area. So this is what it is needed or expected. Now if you see, what you are going to get is that the ranges. Now these are for the rural classification of road. Now for the urban classification of road, arterial and subarterial, the cross section, if you see, there are going to be curves on either side of the roadway, and also there are going to be footpath on either side of the roadway. So that is what is expected. So based on that, basically you need to calculate the right of way. And then in the urban setup, another thing is that the road is not going to be elevated, or you won't see embankment on the urban setup. So you are looking at pavement or the carriageway width, some distance for the side distance they call it from the curb side, about 0.15 meter or so on either side, and then there is a footpath which is about going to be, depending on what is the standard they are going to follow, it can be up to 1.5 meter to 2 meter, and in between the two direction there could be a median. If there is a median, it is going to be 1 meter or 1.5 meter, and altogether whatever it adds up is going to be your total right of way with minimum which is needed. And then there are various other concepts of the cross sections in the urban setup. So sometimes they provide a green barrier between the travel path and the pedestrian. So that will depending on what is the width they're considering. The green barrier means they will plant trees and other things. So those needs to be considered. So now let's move on to the super elevation. So the overturning effect, as we told that the load, P is equal to WV square by GR. Now here, if you see in this figure, basically the centrifugal force is acting in this direction and the weight is acting in this direction. So the centrifugal force and the moment it is creating is the centrifugal force acts from the center of gravity of the this vehicle. So the moment, the overturning moment it is creating is P times H. So that is what the centrifugal this is the moment for the overturning. And how it is being restored? It is restored by the weight of the vehicle which is acting downward. Now when it is acting downward, the hinge point or the this point is here. So if it is acting downward means it is and the wheelbase is about, if it is B width, so this is half of the base width, and this is the moment is going to be W times B by 2. So this is what the restoring moment is. So in equilibrium condition, the restoring is equal to the overturning moment. So that is why you can see that P times H is equal to W times B by 2. Now if we consider this P by W, it becomes G by 2H. Now the danger of overturning, or basically when it is going to overturn, when P by W is greater or equal to B by 2H. So if you recall the previous slide, we said P equal to W V square by GR. So P by W is equal to V square by GR. So that means we are saying that V square by GR should be, if it is greater or equal to B by 2H, there is a chance that there is a danger of overturning when this due to centrifugal force. So we said two things. One is the overturning, the other is the lateral skidding. So when we say the lateral skidding, basically this is what is happening. In the lateral skidding, the load which is here, it is acting in this direction, and it is counterbalanced by the friction which is in this direction. So the friction part, or the this part is actually the friction at the bottom of this wheel and the bottom of this wheel. So together it's Fa plus Fb, and this Fa plus Fb is nothing but the friction factor or the coefficient times the total reaction. So total reaction is Ra plus Rb, and the total reaction is nothing but the total weight of the vehicle. So that is W. So F times W. So this is your friction, the skid resistance due to friction. In equilibrium, what is going to happen? This load or the centrifugal force is going to be equal to the resistance, which is this F times W. So P is equal to F times W. So again, if we put back to this equation, P by W, which is equal to V square by GR, should be, if it is more than F, then there is a danger of skidding. So in summary, what we are looking at, if P by W is greater or equal to V by 2H, then there is a chance of overturning, and if it is greater or equal to F, there is a chance of skidding. Now how to counteract this? We provide a banking, and this is called the super elevation, and this we provide it in the outer edge of the pavement, and once we provide, this helps to balance the force to some extent, and that you will see in this next slide. Here the picture, if you see this, the outer edge, we are providing this banking or the super elevation. So when the curve is here, we are providing this super elevation to counteract this. So how it is going to work? Let's look into the equation now. So when we provide this super elevation like this on the outer edge, and the basically the curve is on this direction towards the left, like this. So in this case, again the centrifugal force is acting horizontally and the load is acting downward straight, and this is the slope of the pavement. So if we look into the slope of the pavement, we need to find out what is the rate of super elevation. So the rate of super elevation is nothing but tan theta. So tan theta is NL by ML. So this is what your rate of super elevation. So irrespective of the pavement width, you can, if you know the super elevation, you know how much you need to raise the outer surface. Now, being theta, it's going to be very small. So if theta is very small, what is going to happen? Tan theta is almost equal to sin theta. And if we say it is equal to sin theta, it is actually, then we can say this elevation, whatever we are providing in there, divided by the width of the pavement. So this is your width of the pavement. So E by B, E becomes E by B. Now you know what is the width of the pavement. Based on that, you can calculate how much you need to raise. So this is about the rate of super elevation. Now let's look into the forces, how it is acting. So as I told you, the P is acting horizontally outward and weight is acting vertically downward. And now if you want to balance, basically in equilibrium, if you say, which is along the surface of the road, so P component on this direction is P cos theta. And it is balanced by the W sin theta and the friction force. So W sin theta is going to give you in this direction and the friction force. And if you, the other thing, and this friction force Fa and Fb is going to be maximum, is going to be total of the load. Now let's look into this part. What is the maximum reaction you are going to get? So the maximum reaction is you are going to get from this is the P sin theta, which is the component of P in this direction, in the perpendicular to the pavement surface, and the W cos theta, which is again perpendicular to the surface. So the total of these two is going to be the total reaction on the these two tires. So that is your Ra times Rb, Ra plus Rb. So this is what you are getting. Ra plus Rb is equal to W cos theta and P sin theta. So Ra plus Rb is, if you want to see from the friction force, it is actually the friction force is friction coefficient times Ra plus Rb. That is what the friction force is times F, or the friction coefficient times Ra plus Rb, which is W cos theta and P sin theta. So ultimately we are getting Fa plus Fb is equal to this equation. Now we have seen this equation, and Fa plus Fb we are seeing this equation. So if we move on to the next slide, we'll see that how we can consider. So if we replace that Fa plus Fb in the first equation, then we can easily rewrite this equation P times cos theta minus F sin theta is equal to W sin theta plus F cos theta. So in both cases, if we divide by W cos theta, we are going to get P by W times 1 minus tan F tan theta equal to tan theta plus F. So now we are coming to this P by W is equal to this equation. Now if we recall that IRC recommend the lateral friction is going to be 0.15 and tan theta is very small, and it is we generally provide up to maximum of 7% of super elevation, so which is going to be 0.07. So if you multiply these two parts, means F times tan theta, it is almost 0. So if it is almost 0, then 1 minus F tan theta, this can be considered as almost equal to 1. So this is how we are deriving, and then we are getting P by W equal to tan theta plus F. So tan theta, again if you go back, which we said tan theta is quite small, which is equivalent to sin theta, and sin theta is equal to E. So all this thing is coming here. So it is E plus F, P by W. And earlier we said that P by W is nothing but V square by GR. So at this equilibrium condition we are getting V square by GR is equal to E plus F. Earlier, if you recall, that the overturning or the skidding is going to happen when V square by GR was greater or equal to E the V by H or greater or equal to F. Now we have, along with F, we have added one more parameter, E plus F. So this is going to enhance the safety in this case. So your V square by GR should be always less than this, and the rope is going to be safe. So how we look into this? Basically, the IRC had provided a design chart like this. There is a design speed, and you know what is the radius of meter, and this is what the percentage of super elevation which is need to be provided. So if you know the design speed, if you can find out radius, what is the camber you are providing. Okay, so this is actually the maximum super elevation. We'll come to this one. So there is another chart. So there is a maximum super elevation and minimum super elevation. So maximum super elevation is the super elevation which you need to provide, because if you provide too much super elevation, yeah, if a vehicle is traveling at a higher speed, it is good, but you cannot expect that the vehicles are going to travel at a higher speed and all the time. And also in India, there are not in India, everywhere there are mixed kind of vehicles. Heavy vehicles which will travel at a lower speed, and there are lighter vehicles which will be traveling at a higher speed. So we need to have a balance between these two. And when you have a balance between these two, basically you need to consider what is the maximum limit it's going to be. And the maximum limit as per code, it is going to be 7%. So, and what is the minimum thing? So minimum, if you recall, like we had provided camber to drain off the water. Now, if you estimated when you calculate your super elevation and found out that your super elevation rate is less than your camber, then definitely you need to provide the camber, because you want the water to drain off. So this is why at certain radius you don't need to provide super elevation, and this is what this table is about. Radius beyond which super elevation is not required. So if your design speed is this, and if your camber is this, so if your radius is more than these values, then you don't need to provide camber. So for example, if your design speed is say, suppose 100 and you are providing required camber is say suppose 2.5%. So if your radius is beyond 1800 meter, then you don't need to provide any super elevation. If it is less than that, you have to estimate the super elevation and provide that. So this is how it's going to be. So I see one question though, what disadvantage of camber. So the disadvantage of camber, as I was trying to mention, was that if you have high camber, basically it is going to affect the driving comfort, and you will see that the drivers are actually driving through the middle of the roadway, so that they are quite balanced and they don't have this tilting effect on the side of the roadway. Okay, so I got another question. It's a very interesting question, that how the radius of curve is calculated in the racing field or in expressway where speed is very high. So the way this radius is calculated, that is what I will be discussing now. And in the racing field, it is expected that the speed is not going to be less than certain speed of the vehicle. So if you are considering a racing course where the average speed is 150 kmph or more, basically you will be providing a camber more than 7%, because you won't expect someone to be traveling at 20 kmph or even less than 30-40 kmph. So, but whereas in a real life, in a national highway and those, you will get wide spectrum of speed. Some vehicle traveling at 40 kmph, some are considering traveling at 80 or 110 kmph, and accordingly you have to consider the overall mix. And this is why there is a limit for the higher value. And another question before I move on to this super elevation design is regarding the camber. Does camber depend on the quality of road surface and subgrade? The road surface, yes, it do depend on the road surface. As I told you, the bituminous pavement, if it is porous, means you are going to provide more camber. Whereas concrete, when it is impervious, you are going to provide less camber. So it depends on that quality. So I'm getting question before I started teaching something. So the question is, why do we take 75% of the design speed of super elevation? I hope it is better to wait after I teach, and then you ask the question related to that. Since you are seeing the slide, you are asking question. Okay, so basically now we'll come up with the design step, how to estimate the super elevation. As per IRC, what we say is that you consider the 75% of the design speed and find out what is the super elevation. And when you are considering the 75% of the design speed, you are totally ignoring the lateral friction. And this is why you are considering 75% of the design speed. So definitely there is going to be some lateral friction, and as we had discussed, lateral friction, there is a lot of safety inbuilt into that, because we are only considering 0.15. Not 0.35. It's the same material, you know, as per the physics property, the friction coefficient is going to be same in all directions. However, it's the same pavement and the same tire which is having two different friction coefficients in two different directions. And so the lateral direction we keep it low just to make sure we are in the safer side. And so the process here works this way, like we consider the 75% of the design speed, neglecting the lateral friction, and based on that we put into that equation which was like E plus F V square by GR. So now V is equal to 0.75, which you see here, and F we have considered 0. So since we had considered 0, we have considered 0.75 here. Based on that, we calculate the super elevation E percentage. Now we said that our pavement, the maximum super elevation could be 7%, considering all different kinds of vehicles. So by this calculation process, if you found that your super elevation value is more than 7%, more or equal to 7%, we need to go to step 2. Or else, if it is less than that, we'll be just providing that super elevation, and on top of that, basically we already we have some lateral friction, so definitely the road is going to be safe. So if it is more, then what do we do? We assume that, as we said, we can maximum provide 0.07%. So we provide 0.07% and try to find out what is the friction factor. Now when we introduce the friction, we are no longer considering the 75% design speed. We are considering the 100% design speed. And again, that go back to the regular equation, which was E plus F equal to V square by GR. So there F is equal to that E value we are subtracting on this side. F is equal to V square by GR minus 0.07. So this, once we calculate and find out what is the F value, we see if it is less than 0.15 or more than 0.15. If it is less than 0.15, means good, we are done. Basically, we got our friction or the stipulated friction whatever you need, and we should provide us super elevation of 7%, and we are good to go. What if your friction is more than 0.15? In that case, we have to go to the step 3. So step 3 says that to be safe, rather than doing anything else, means you need to reduce your design speed. So what do? We maxed out our super elevation, we maxed out our friction factor 0.07, 0.15. Based on that, we find out what is our design speed, safe allowable speed, and based this is the equation through which we can find out the speed, and this is what how we should be providing the speed limit, and this will be the design speed, and the speed limit will be lower than that, and this is how we will be designing the overall super elevation. So I hope the process is clear. It's in 3 steps. First, we are looking at what could be the super elevation for 75% of the design speed. Once we know if it is more than, if we find that it is more than 7%, the maximum limit, then we assume it to be 7% and find out what is the friction factor it's going to be for the 100% design speed. So once we find out the design speed is friction factor is 0.15, it's good, done. If it is more, we need to actually go back and revise the design speed, and accordingly we have to find out the post the speed limit sign. So this is the whole process. So before I move on to the next slide, I got one question, which is, why is the pavement of an airport designed as a flexible pavement but not as a rigid pavement? Matter of fact, some of the airport pavements are designed as rigid pavement as well. However, mostly it is designed as flexible pavement because flexible pavement are easy to maintain, first of all, because if there is any damage, you can just take out that portion and do the maintenance. Whereas concrete pavement is actually difficult. You have to saw cut and do it, and then make sure the level is proper. That becomes a lot of headache. The second part is that it's very easy to maintain the profile of the pavement. Recently we received one query, or basically from the industry. They constructed a airport or pavement, concrete pavement, and they found that the level was wrong, and some place it was there is a water stagnation. Now how to repair this? So this becomes a headache. Now if it was your bituminous pavement, they could easily actually overlay and make it level. So definitely there are other lot of issues like this. The other thing is that if you see the right quality, and the bituminous pavement provide better right quality than the concrete pavement, because the resilient modulus and this concrete pavement is quite hard compared to the bituminous pavement, and it is quite bituminous pavement is quite flexible and it's provide better right quality. So these are the various reasons, and you can explore more reasons, and there are more lot of other reasons as well. Now we talked about the super elevation, how we should design this super elevation. We know how we should provide this super elevation. We had already provided a camber, which is the cross slope on the roadway, and if you see, the cross slope is going to be like this. Now we need to provide a super elevation, which is ultimately one side is going to be higher than the other side. So there are two ways of attaining this super elevation, and the two ways actually consist of two processes. So one is first we need to consider the elimination of crown, and then we need to, once we eliminate the crown and make sure that the pavement is at the same level of the minimum camber, then we further rotate it in the pavement to make sure it is actually up to the level of super elevation. Elimination of camber can be done in two different ways. So elimination of camber can be done this way, like you raise the outer surface gradually and make sure it comes to this level of the existing camber on the other side. Or basically the center point, you keep moving this center point as the road progresses, and then you eliminate it like this. So this process, if you see clearly, one side is becoming steeper than the other side. This can lead to some issue. Whereas this process is smoothing out quite easily and easier to construct and easier to handle. Now once you attain, this is actually right now your this slope is equivalent to the camber. Now you need to attain the super elevation. Your super elevation is actually more than your camber. So camber is 2.5% and maximum is going to be 3% for bituminous pavement, and you have seen that your super elevation can go up to 7%. So in those situations, how we are going to do it? So again, there are two processes. The two processes is that once you attend it up to the camber, now you need to rotate. So the rotation of the of this pavement can happen either from the center point. So if you are doing it from the center point, one side is going down, other side is going up. Or it can be hinged at the edge and the whole thing can be rotated in this way. Again, there are pros and cons for this process. And the pros and cons for this process, if you see, is that in this, when you do the center rotation, one side going down, another side going up, basically you will see that in this process, what is happening? Your earthwork, you are going to actually cut this section and fill this section. This is going to be quite balanced. So earthwork is going to be balanced. And however, what is going to happen? Your ground level is here, and you are putting this pavement surface the lower side. So that means there is a chance of water stagnation at this location. So you need to have a good drainage. If you actually hinge this point, the inner side and outer side, you keep on raising, what is going to happen? Then this side is actually at the level of the ground, and this side is raising, so you don't have the water stagnation issue like what you have here. So once you have this thing, but the problem is the earthwork. So you need more earth from outside, not from the same region, to borrow it and fill it to actually construct it. So this is the two types of rotation, and you choose according to the condition and the what is required there. Now let's look into the overall highway, how we are attending. So here you can see the curve where you have, and as I told you, in between the curve and the tangent portion, there is a transition curve. So in the transition curve, actually this super elevation is added. So in the tangent portion, you have a camber like this. Whether it is going to be straight line or going to be parabolic, it's going to be like that. So in the transition curve, so first you eliminate the camber, and then you provide the super elevation. By the end of the transition curve, and when it starts the circular curve, you attend the full super elevation. This is what is provided along the curve. And once the curve ends, again you go back the reverse way, gradually you reduce and go back to the camber like this. So this is the overall how we attend the super elevation in a. So now if I before I move to the next slide, I got another question saying that is there any need to provide camber separately even after providing super elevation on mountainous terrain? So if you see your super, now I think looking into this picture, it is clear you are not providing camber and super elevation together. Either you are providing super elevation or you are providing camber. Camber is in the tangent section, super elevation is in the circular curve section. And if you recall the table, we don't need to provide super elevation if your super elevation rate is less than the camber. So I hope I can answer. The other question is how do we provide banking at rotary intersection? So this is related to the intersection design, and the rotary intersection, if you see, mainly it depends on which direction the drainage is. Mainly it is provided outside, and the inner side is quite higher, so it's actually the reverse side or negative super elevation sometimes it is provided. And you have to always understand that the rotary intersection, the speed is quite low. We are not talking about speed of 50 kmph and 100 kmph where we do need the super elevation. So at a lower speed, the camber itself or any slope which is going to help to drain off the water can be easily accommodated in whichever direction it is needed. So now let's move on to the next slide. So the other component, whenever we have this curve, we need to provide extra widening. So what is happening? A vehicle which has a rigid base, the rear wheel doesn't track or follow the path of the front wheel. So when the vehicle is traveling, this is what is exactly going to happen. The front wheel, if it is following the blue line, the rear wheel is actually following the green line. And so there is a difference between this, so which is, we call it as a off-tracking. That means the pavement width is no longer is based on only this front wheel width or the width of the vehicle. It is also you have to accommodate how the off-tracking is happening. Now this off-tracking, the amount of off-tracking depends on the length of this wheelbase, because if it is too long means you can see the off-tracking is going to be more, and also the angle of the turn. So these are the primary two factors. The other how to accommodate this and how could we estimate this, I'll show you next. And then before I go to the next, I got a question, which method of attending of super elevation is used in field during construction? Both methods can be used, whatever method is discussed. It depends on the field situation. If your pavement is on embankment, means you are borrowing material from outside for the whole thing. So in that case, you can you can rotate your pavement based on the inner edge or center, or based on the center as well, so that you can balance out. You need less material for that. If your pavement is or basically if your formation is in a urban type of setup, then it's actually a plane, and you need to balance out, you need to make sure that you have quite good drainage. So it's not embankment. So in this case, we would like to have it on the inner edge side. So it all depends on the field condition. There is no one straight answer to this. So now let's move on to this slide, widening of pavement. So as we said that the widening of pavement we need to provide for various reasons. So at speed higher than the design speed, it may so happen that the outer and the rear wheel may skid more, and it may not only remain on the inner side, but it can also go on the outer side. And already I told you that the wheel path tracked by the rear wheel are not same. So basically the path traced by the wheels of a trailer, in the case of a trailer unit, may be on either side of the center path, because it can skid on the left or right. And also, as a driver, to have a greater visibility, they tend to go on the outer side of the curve, and in that process actually they are using on the additional width. And apart from that, this is for the psychological comfort and other part. The vehicles, when they are overtaking each other, they want to keep more distance than what they are used to keep in a tangent section, because here the control of the vehicle matters. So these are the various factors why we need the widening of the pavement. Now, how do we estimate this? As we told you, like the extra widening, it depends on the length of the wheelbase, radius of the curve, and there is a psychological component to that. So the overall, if we look into the process, there are two components. One is the mechanical widening, to accommodate the off-tracking, and there is a psychological widening. This is provided to greater maneuverability at higher speed, and this also allows to extra overhang of the vehicle, and then it also provides a greater clearance for crossing and overtaking. So one thing you have to remember, that the psychological widening, we need it when there is more than one lane. So when there is more than one vehicle involved in the same travel path, carriageway, then we are going to consider the psychological widening. So if there is if there is a highway which has only one lane in each direction and it is divided by a median, so there is no interaction between the oncoming vehicle and there is no passing activity happening in this highway, so you don't need the psychological widening, you just need the mechanical widening. So how to estimate this? Here is, or let's look into these images. Widening in this curve, so you can feel that here the width is more than the other tangent path. Here also you can see, and this travel path, if you see this black portion, you see that they are going in the outer side compared to the inner side. So this is little bit of imbalance. So this is why we are providing the extra widening. Now before I go to the mechanical widening, I got another question. If super elevation is not provided, then what happens? If super elevation is not provided and if the lateral friction cannot accommodate the centrifugal force, basically the vehicle is either going to overturn or laterally skid, and it can meet into accident. And that was the main point which we discussed at the beginning of the super elevation, why we need the super elevation. So the mechanical widening, we are looking at it. This is what it is happening. As I told you, the front base is not and the rear base, wheelbase are not following the same track. So how do we estimate this? There is a difference between this, the widening, the mechanical widening, the difference between this is Wm, and the radius followed by the front wheelbase and the rear wheelbase, we consider it as R2 and R1. So this widening is R2 minus R1. So this is R2 and this is R1. So this will give you the mechanical widening. Now, if we consider this as a triangle, which is 90 degrees like this, so this is OAB triangle. OAB triangle. This will give you like R1 square, which is this one, is equal to R2 square minus R1 L square. So L is the wheelbase. So from this you know R1. So if you replace that value, then you are going to get Wm is equal to the widening is equal to L square by 2R. If you replace this value with here, and then this becomes your for one lane, this is the extra widening you need to provide, and for n number of lanes you are going to provide n times of this width mechanical widening. So the mechanical widening is Wn and is equal to n times L square by 2R. So next part is the psychological widening, and as I told you, if there is more than one lane, we need to provide the psychological widening, and this is coming from an empirical formula. IRC provided this empirical formula, and the psychological widening is V by 9.5 root over R. And in case, so V is in kmph and R is in meter. So the total widening we need to provide adding these two, and this will give you the total widening. So, so here we are considering there are at least two lanes, and this is why we are adding this psychological widening. And from this we can easily calculate the total widening required and the curve. Now the L is the length of the wheelbase, the longest. Generally, if it is not given, if you don't know, it can be taken as 6.1 meter or 6 meter for commercial vehicle, and then it can be estimated. So this is for the extra widening. So we already talked about the super elevation and the curve radius we had discussed how to get that, and also we looked into this the extra widening which is needed in the curve. So next we'll be moving into, okay, so this is the extra widening. How do we provide the extra widening? So if it is a milder curve, this is how we provide extra widening on both sides. So equal amount of extra widening on this outer side and inner side. If it is a surf curve, we provide it in mostly in the inner side. So there is no extra widening on the outer side. Because in the surfer curve, vehicles are going to travel at a lower speed, and when they are going to travel at a lower speed, we won't see the slipping or skidding of the rear wheelbase. So as I told you, the rear wheelbase can be outer side or inner side depending on the speed. So that is why we are providing on both sides. Whereas in a surf curve, it is always going to be on the inner side. So this is how it is being provided. So before I move on to the next section, I got another question. Can extra widening reduce road accident? It depends on what kind of road accident it is. If your road accident is happening like side swiping on the curve, yes, it can reduce road accident. If your road accident is actually off tracking, basically the vehicle is actually overturning it, or it's going off the road, the extra widening is not going to help mostly. So it's more with, and you have to deal with the super elevation and the radius and the speed. So we talked about the extra widening. Now we'll go into the horizontal alignment. With all this basic information, how we can design the horizontal alignment. So if you look into the horizontal alignment, these are the various combination of the tangent section and the curve. So this is what I am telling you again, that the horizontal alignment is actually combination of the tangent section and their curve. Now it depends on how these curves are combined and we put it. If your curve has a simple one radius, it becomes a simple curve. So it's same radius also. There could be a situation you may need to provide two different radius within the same curve, and this becomes a compound curve. It started with radius R1 and it ended with radius R2, and this becomes a compound curve. There could be a situation where you need to provide a short tangent between the two curves, and when you provide this, it looks like a broken back. So this is why we call it a broken back curve. The other thing could be like you may have curve on two different directions, and this can lead to a reverse curve situation. So in reality or in design, we will try to avoid all these three: compound curve, broken back curve and the reverse curve. Some of the situation may arise, you may need to provide one, and this, when you use this type of, you have to design with caution, but mostly we'll be dealing with the simple curve. So if we look into the few basic elements of horizontal curve for the design purpose and the layout purpose, these are the few things which you need to know. The tangent length. So the tangent length from the PI where the tangents are meeting, which is, we call it as the point of intersection. From there where we need to find out the distance where the curve is going to start. So this T is equal to R times tan delta by 2. Delta is the angle or the deflection angle of the tangent. So this was the one tangent, this is the other tangent. So if you see, the road is actually deflected by this amount of angle. So once it is deflection, this is the deflection angle, and this is what we are going to use, R times tan delta by 2. So chord length, we need to know the chord length means this is my chord, this is my chord length which you need to know. What is my chord? So the chord length, if we find out, we can get it by 2 times R sine delta by 2. So if we, this one is R sine delta by 2, from this you can see the triangle, and this is twice of it as per the circular curve property. We know this is going to be twice, so this is 2 times R. Mid ordinate. So the mid ordinate, you need to remember this formula because this is quite useful. We will be looking at it, the setback distance for the side distance. We need this thing again and again. So it is, if we know this is R minus cos and delta by 2, this is R cos delta by 2, this will give you the mid ordinate. Then we also need to know the external distance, which is this E. This is again for the curve set up in the field. So if you know this tangent, how are you going to set up from this point? This is the distance. So you need to calculate. So R set delta by 2 minus R. This is how you are going to get. So these are the basic formula, and this can be easily estimated if you know all these angles, and this is coming from the basic geometry. Now once we know that, we will move on to the next one. Before I move on to the next one, I got another question. For a multi-lane two-way national highway like 4-lane or 6-lane, is it necessary to provide extra widening? Of course we do need to provide extra widening because the mechanical widening is needed to ensure that this extra widening is for each lane. So you need to accommodate, you want to make sure that every lane is 100% utilized. You don't want your vehicle, half of the vehicle in one lane and the rear part of is going to the another lane because of this curve. So that is why you are going to provide extra width there so that the complete vehicle is in the same lane. So as I told you, we'll start with the setback distance. So setback distance, like when on the curve, a vehicle as it is traveling, it is trying to see what is there ahead of it. So once it is seen, the view can be blocked by any object which is on the view path. So if it is blocked, means they can only see up to this much, and it may not be enough for stopping. So they need the complete distance for the stopping. And this is why we need to see how far these buildings are going to be from the roadway. And once we know this thing, we need to also, that becomes your right of way as well. So how do we calculate this? We'll go one by one. There are two different situations. The first situation, when the length of the curve is actually more or equal to the side distance. And within that, there are two different situations, which is you have a single lane roadway or you have a multi-lane roadway. So when the length of curve is more than equal to side distance, and if it is single lane, you know the angle here, or this angle alpha is going to be S by R radian. It is again coming from the geometry. So if we convert this radian into degree, 180 times S by pi R. So we already know that M is equal to, the mid ordinate is equal to R minus R cos alpha by 2. So see, this alpha, whatever we get here, we replace it here and we put it. So S, as I told you, the curve length is actually more than the side distance. So we are only considering the side distance. S is the side distance. So if we know this, we can actually estimate it. Now, the other thing it can happen is the multi-lane. So in multi-lane, what is going to happen? We have more than one lane. So you have to consider it for the worst case. And when we have more than one lane, the radius is for the central line of the roadway, which is here. So your central line is here, but you have to consider the worst case. So worst case is like when the vehicle is in the inner lane on this side. Then what is going to happen is that you are expected the driver eye or the vehicle center position is going to be the center of this lane. So in order to estimate the distance, this r is no longer going to be r, it is r going to be r minus d. And what is d? D is the distance between the center line of the roadway and the central line of the innermost lane. So if you have two lanes, one lane on this side, one lane on this side, your center is here. From there you just need to d is going to be 3.5 meter divided by 2. So that is your d. If you have 4 lanes, means 2 lane on this side, 2 lane on this side, your radius, this radius is up to the central lane. So you have to cross 1.5 lane. So 3.5 plus 3.5 by 2. So that is your d. D value will be 3.5 meter plus 3.5 meter by 2. That is how you are going to estimate. And once you put in there, this formula remains same, r minus r cos alpha by 2, where this r is actually r minus d, because we are considering this distance. And then alpha is this angle, whatever is extended here, this angle, and based on that you are going to estimate. So here this figure it is showing theta, but this is actually alpha, the same angle, theta is equal to alpha. Now the situation is different when your length of the curve is actually less than the side distance. So what is going to happen? You need to see the object while you are still in the tangent portion, and in this case you have the distance which comprises of your tangent portion as well as curve portion and again tangent portion. So your angle is only this much, right? So that angle when you are estimating is alpha is equal to LC, which is your length of the circle or the curve up to this much, divided by r minus d. The way we calculated r minus d for a multi-lane, if it is single lane it's only r, that radian you convert it into degree. Now here is where you need to consider. So here this equation is going to take care of this ordinate. So if you draw a line here, so at this point actually I'll be using this board. I need to make sure that this camera is useful. I need to use the camera, this one. So here basically there are 2 components. If you see, one is the curve component and this tangent component. So this part, this equation, r minus d cos alpha by 2, this component is going to take care of this one. So we are talking about tangent, then there is a curve, and there is a tangent. So the first part of the equation which you saw, this m value is going to take care of this r minus d cos alpha dash by 2. Okay, so this is the first part. Now we said that our side distance, because the length is less than the side distance, your s is totally this part, side distance. So you also need to calculate this distance as well. So this is the other distance you need to calculate. So I'll say this one m1, this is m2. So m2 you are going to estimate. M2 is equal to 0.5 times s minus LC. So LC is this part, LC, and the total from here to here is your S, right? So this is S, means this portion is your S minus LC divided by 2, and this is again S minus LC divided by 2. So this is what it is. The next part is you need to calculate this distance. So this is your sine alpha by 2. So again it is coming from that angle, whatever this angle was alpha. So this alpha by 2 you are going to get, and from there you can estimate this m2. So m dash is equal to m1 plus m2. Then you are going to get the whole equation which I showed you, which is r minus d times cos alpha by 2 plus 0.5 s minus LC times sine alpha by 2. So this is the way it is calculated. So now once we know this one, we can find out this equation, and we can use this equation for estimating that offset distance. So IRC actually provides this kind of table which makes life easy to estimate. You can find out what is the speed, and you can see what is the stopping side distance, and from there radius of horizontal curve, and you can find out what will be the setback distance. So speed, side distance, and all those things are given, and you find out the curve and you find out that distance. So now let's move into the other part. As said that there is a curve and there is a tangent. So in between we are going to provide the transition curve. Why do we need the transition curve? Because we need the driver to gradually change the speed from the tangent to the curve section, and also they need to nicely transition their steering position as well. So in the in the tangent position, they are holding the steering straight, and in the curve they need to rotate at certain angle. So this rotation will, if you rotate it gradually, then you won't feel the jerk. But if you rotate it all of a sudden, then you will feel a jerk. So this is why we need to have this gradual transition. And when we do that, basically we need to provide the transition. Apart from this, you need to recall that when we said we are going to provide the super elevation, and when we provide the super elevation, it needs to be gradually attained from the temper to the super elevation, and this super elevation is to be attained before the curve starts. So how do we do that? This is actually happening in the transition curve. So for that also we need the transition curve. So when we provide the transition curve, it also provides a aesthetically better appearance. So if you see the top figure, if there is no transition curve, a driver will see this kind of thing right here. So this vehicle, wherever it is going, you need to see this type of thing. Whereas if we provide the transition curve, a vehicle will see a smooth alignment like this, and it's much more pleasing and easier to drive from the psychology point of view. So what are the different shapes of transition curve we provide? The various shapes of transition curve we provide are the spiral, lemniscate, and cubic parabola. Now, any of this transition curve, whatever we provide, we want to make sure that if the radius of a tangent is infinite, whereas the curve has certain radius. So the property it should have is like that the radius of the transition curve that should vary from infinite to the desired radius, and it should also come as in the proportion to the length. The transition curve must be in proportion, inversely proportion to the radius. So this is how it can be attained. So if we do this, this is the ideal requirement, and based on that we have found out these are the three different type of transition curve. Many times we provide the spiral, and sometimes we do also provide the cubic parabola. It depends on how it's estimated and how it can be done. Now once we put the transition curve, our main circular curve is going to shift little bit inward, and this is the earlier if it was connecting the tangent portion here, it will be due to the tangent, it will start from here little bit, offset is going to happen. So this can be easily done with the calculation, and nowadays with the software this can be easily been fit in, and it can be used. So I am not going in details about how to fit in a transition curve because that itself will take some time to do. But there is a transition curve, and how we select the transition curve and how it is being fitted, that I just showed you. Now coming to the length of the transition curve, there we need to look into various factors. Now the various factors which we need to look into are based on the objectives. One is the rate of change of centrifugal acceleration we need to make sure it is developed gradually. The second thing is the rate of introduction of design super elevation. We have already discussed the super elevation. We cannot just provide a super elevation like that. It has to gradually be introduced, and there is a rate for that, and how it can be accommodated that, and there is a minimum length. So the rate of change of centrifugal acceleration, based on that, if we try to find out, as per IRC, it says that the rate of change of centrifugal acceleration, the C is between 80 by 75 plus V, and it should be between 0.2 and 0.8, and V is the design speed in kmph. If C value is within this, then this is a comfortable rate. And if we know this comfortable rate, the centrifugal acceleration, then we can easily find out from this formula, MPP formula, by LS equal to V cube by CR, or if it is, this V is in meter per second, this is in kilometer per hour. So if you convert this, then you will get a, for the comfort level, we will get one transition length. So this is equation 1. Equation 2 is based on the rate of introduction of super elevation. So as we told you, there is a rate of super elevation, how we should be introducing. The minimum value as per IRC is given 150 for the plain, and for the rolling, and 60 for the mountainous or steep terrain. So this is the rate at which the super elevation should be attained. Means you ease the camber, and from the camber you need to provide the super elevation. This is what you need to consider. So if you know the super elevation, what is there, you can estimate this. Now there are two options of doing that. You can either rotate it based on the central line, or you can rotate it based on the inner edge. So if you are rotating it based on the central line, you need half of the length, because one side is going down, another side is going up. It is actually attaining it in a twice rate. So this is why you need the half of the length. So it is E times N by 2. N is the rate, and E is the super elevation which you need to provide. And this super elevation is nothing but E is the super elevation rate times the pavement width plus the extra widening in that pavement. So together you can get it. Now if it is happening in the based on the edge side, in that case it's happening in one side only, and then it is not divided by 2, but this is the formula, and this is the way you can find it. Now the third type is again another empirical formula. For plain and rolling terrain, the IRC says that the length of super transition curve is going to be 2.7 V square by R. If it is a mountainous and steep terrain, it is going to be just V square by R. So we are going to get 3 different values for this, and we are going to choose the highest of the 3 values, and that is what we need to accommodate. So this is how we do the transition length. So before I move to the next slide, I got a question: which type of transition curve is preferred in construction? So it depends. Either type, any type is good, because all these calculations are done in the design, and when they do the design, they say what is the offset at different location is going to be, and in the field, in construction, it is easy to construct any of these as long as those values are given. So another question is in slide number 47, graph showing different types of transition curve. What is X and what is Y axis? So let's go to the, yes. So this is your, this transition curve is what did I say is this is your major axis, and this is your X and Y axis, both are in distance. So both are in distance means if you are looking into the XY plane, because this is which we are providing in the horizontal plane, horizontal alignment. So if you have a tangent section which is coming from here, and this is what you are fitting, and this is where the curve is. So both are actually in meter or centimeter, whatever unit you can say, and because this is for the horizontal alignment. So we know how to estimate the transition length. Now there is a IRC specification which says that what should be the minimum transition length based on the design speed and based on the curve radius for plain and mountainous. And all this thing is based on those 3 equations which we said, and the minimum, the maximum value from there. So if you use this table, you can get the transition length in one shot, and you can look into the design whether this has been provided or not. So next we'll be moving into the vertical gradient, and I think in 5 to 10 minutes we'll be ending this vertical gradient. So the vertical gradient, we talked about the horizontal alignment. Now in the vertical gradient, we are going to see how wherever there is an elevation difference, how we can accommodate that. So what it is ensures that it's change in the gradient from one section to the another section, and the gradient is nothing but the slope of the roadway in the horizontal direction and it vertical curve establishes a transition between the two roadway grades. So if you may have two roadway which are of two different grades, and this vertical gradient will help you do that. Now the vertical gradient, if it is an ascending, it is noted as positive. If it is descending, it is noted as negative, and it is either noted as in percentage or one in certain level, one in value. And if you see, this is how it is going to be. So if it is 100, then it becomes in percent. If you know the value 1 in n, this is how it is going to be. So these are the various ways. Now what are the different gradients we see on the roadway? We see these are the 4 different gradients. One is the ruling gradient, another is limiting gradient, another is exceptional gradient, and the 4th one is minimum gradient. So we'll go one by one, these various gradients. The ruling gradient, it is the gradient which the designer wish or they want to use for the gradient. This is the maximum gradient they want to provide, and or they provide in the design. And it depends on the terrain, it depends on the length of the speed and pulling power of the vehicle, which is the traction, which we discussed earlier as well, and the presence of horizontal curve. So if we look into the other type of gradient, those are the limiting gradient and the exceptional gradient. So this ruling gradient, as I told you, this is what a designer wants to put the gradient with. The maximum gradient should be within the ruling gradient. And however, in certain situations, due to extended earthwork or some restriction or constraints, they need to provide more than the ruling gradient. So this is because of the when the topography or the plane compels of adopting steeper gradient, we need to provide the limiting gradient, and this limiting gradient is higher than the ruling gradient. So length, and we try to make sure that the length of the this continuous grade line is given the ruling gradient should be limited. It's of limited length. You cannot just provide a ruling gradient for longer stretch. Apart from the limiting gradient, you may sometime as a designer you may need to provide the exceptional gradient, and this is again going to be for a short stretch. So if you see the short stretch we are talking about, it should not be more than 100 meters, and this is morely limited in the mountainous and the steep terrain. And if you are for the design issue or for some constraint, if it is not provided, you can provide exceptional gradient. So now we can look into the various. So the last part is the minimum gradient. We do need to provide some gradient for the drainage purpose, the longitudinal drainage. The lateral drainage, we are providing this camber from the top of the surface, and which will take care of that. But from the longitudinal, we need to provide some gradient. This is why we need to provide the minimum gradient. And it depends on the rainfall, and again the climate condition plays a role here. It depends on the soil type and the other site condition. So what is this value? The minimum value is 1 in 500, and if we are providing the concrete drain or the line drain. And if it is a soil drain, you need a little bit steeper, so which is 1 in 200 or 0.5. So this is what the minimum gradient is. So as per IRC recommendation, these are the values for the plain and rolling terrain. The ruling gradient is this 3.3, limiting is 5%. So various terrain, these are the various gradients, and accordingly the designer used the gradient to keep the gradient within that value. Now the one more concept which is going to be there is the critical length of the gradient. We are talking about the critical length all the time. what should be the length of this. So the maximum length of ascending gradient for a loaded truck can operate without reducing in speed. So if it is reducing the speed, means that is not good. If you need to make sure you need to provide a length in which the vehicle, the truck are not going to reduce the speed. So if you are providing more than 100 meter, which has been seen that for the this exceptional gradient, the truck's speed is going to be reduced. So that is why we restrict it within 100 meters. So that becomes your critical length. So for each gradient, you need to find out what is your critical length. If the reduction is up to 25 kilometer, it is considered reasonable and acceptable. If it is more than that, it's not acceptable. And critical length of ascending gradient should be limited to short stretches. So again, it should be short stretches so that again they get a plane area, a planar mild gradient in which they can gain the speed and use that momentum for the next gradient. So in these cases, what happens is that for those slow moving vehicles, you are compelled to provide, and you know that your heavier trucks are going to be slow. What you do is you provide an extra lane onto the roadway and thus higher gradient. So what is going to happen? The extra lane can be used by the fast moving vehicle to overtake, or if the heavier vehicle just move on to those extra lanes, then your main highway is free and the fast moving vehicle can just go use that free lanes to go. And this extra lane is called the creeper lane because the slow moving vehicles are going to creep in this lane. And whenever we are providing this extra lane, the creeper lane, we need to make sure that there is no restriction in side distance. Because if there is a restriction in side distance, means the fast moving vehicle will not know where the slow moving vehicle is, and they will also not know where the creeper lane is. So that becomes a safety hazard. So this is the reason actually the lane should be initiated at a point closer to the bottom of the hill. So at the bottom of the hill, when everything is visible, the driver can see and they can move. The other thing is the grade compensation. So if you have a curve on the and also a gradient, then you need to provide some compensation for that, because the same traction force is going to be used for the gradient, and as well as if you see in the curve portion, what is going to happen? The traction force is in the tangential direction, whereas the curve is the vehicle is moving in the between an angle. So for that, it is already losing some force, and this is the effective and this is the effective resistance which is developed in there. And this is so this is already reduced, and again the gradient is going to reduce it. So in order to compensate that, basically you actually compensate the gradient. How do we compensate the gradient? IRC has some specification, and the first specification, it says that grade compensation is not required if the grades are fatter than 4%. And if it is more than that, how we do compensate it? Is based on 30 plus R by R percentage, where R is the radius. So this is you calculate, and that is the amount of compensation you provide to the gradient if it is more than 4%. So and the maximum compensation is 75 by R. So it may so happen that you are providing a gradient of 5%, and you have a curve which after the estimating you found out that your grade compensation requirement is 1.1%. So you know that beyond 4% you don't need it, so you just reduce it by 1%, that will be sufficient, and that can be accommodated. The maximum is 75 by R, so again this also you calculate and compare, and then you use that effectively. So there is one question, I'll take that in the end because this is the last slide. So in summary, basically you look that the ruling gradient is less than the limiting gradient, and exceptional gradient is actually more than the limiting gradient, and the designer generally adopts the ruling gradient, that is what it needs to be provided, and the stretch of an exceptional gradient should not be more than 100 meters. So, and we also need to provide the minimum gradient for the drainage. This is the summary of the gradient. Tomorrow we will start with the vertical profile, the curve, and all those things. So with that, my today's lecture ends, and then I'll start taking the question, and already I have one question. So the question is, can you show the photograph of a creeper lane? Unfortunately, I don't have a people lane photograph, and in India so far I didn't see any people lane as such, even though the total provision is there, but I have seen it in some highways in US where the gradient is too high and they just accommodated one extra lane on the inner side, or basically on the slower side of the road. So this is nothing but you can think about the overtaking side distance zone. So we are just adding one extra lane in certain stretch where the gradient is too high, and to accommodate the people lane. Good morning. We have started with the highway geometric design, and today is our last lecture on the highway geometric design. So far we have covered many different aspects of the geometric design, which includes the horizontal alignment design and the basic cross-sectional details of the horizontal alignment, and the gradient, the planning process of highway alignment, and the overall policy with the highway sector. We had covered all these things in last 2 days lecture. So today's lecture we are going to cover about the vertical alignment of the vertical profile. Before I start with the vertical profile, in my last lecture someone asked about the creeper lane, how it is provided, and if we can provide any picture or any image of that. I tried, I couldn't get any better picture, so I thought of drawing it on my own. So I'm going to share that drawing. I have it here, so soon you will see that um, in this drawing. So this is little bit out of focus, and I'm going to get the technical help to get it focused. And once you see this, you'll see how the creeper lane is being constructed, or how it is being considered. Now you can see the alignment here. So the top part of the alignment is actually uh, this top part is actually your horizontal alignment, and here is the creeper lane which you are going to which you need to provide. And why you are providing this will be clear if you see the vertical profile. So vertical profile, you see that it was milder profile in the beginning, and then and the gradient increased, and if the gradient increased substantially, so that the vehicle speed is going to reduce, we need to accommodate the slow moving vehicles, particularly the heavy truck or other type of heavy vehicles. So when this needs to be included, what we do is like we add one more lane here in the as a creeper lane, where the slow moving vehicle, in our case which is on the left hand side, they will move to this third lane which is right here, and the fast moving vehicles can continue with this lane. And as the grade is again come back to normal after this point, so the creeper lane goes, and now again it is back to 2 lane. So the other direction is this side is actually the other direction, the black part, and we don't need a creeper lane because it is going downhill. So this is how it is going to look like. And we said that the creeper lane should start at the bottom of the gradient and where it is clearly visible. So you can see that where the curve starts, or and where this gradient starts, we are providing the creeper lane right at that access point, so that drivers who are driving in this direction can clearly see that there is a creeper lane, and they can also see the gradient and can get a sense that they are going to get slow. So they will be moving into the, particularly the vehicle which is going to move slowly, they will move to the creeper lane and move forward. So this was about the creeper lane. Now we'll move on to our today's lecture, which will continue. There are gradients we discussed. The gradients are going to change from one location to another, and as it changes at the transition, we cannot just leave it like that, otherwise it is going to look kinky. So we need to actually incorporate a curve to smoothen out that kink. So if in this case you see this, if you just leave it out like this, here is the kink you can see. So to smoothen it out, we actually create a curve. So this is becomes a vertical curve. So this is the first component of the vertical profile, and this curve, according to the gradient, it can be of two types. One is the summit curve, which you see here, like which is convex upward, and the other is the valley curve, which is concave or downward. Now how do we know that whether we need to fit a summit curve or valley curve? That is going to come from the gradient. If you recall last day's lecture, we said the upward or the ascending gradient is referred as positive, and the downward or the descending gradient as negative. Now the change in gradient is always the difference in the gradient from one to another. So the algebraic difference, if you see, that difference is actually positive, then you are going to get a summit curve. If that difference is negative, you are going to get a valley curve. So here are 4 examples or the 4 instances when we are going to get a valley curve, a summit curve. So in this case, the positive Ni means which is ascending gradient is steeper than the other ascending gradient which is N2 when the grade changes. So definitely the difference is going to be positive. The second case, in this the positive gradient is actually matching with a flat gradient which is 0, N2 is equal to 0. So definitely the difference is N1 and the N1 is positive, so it is a summit curve. Likewise here positive meets with a negative, so the difference is going to be positive because N1 plus N2. So this is definitely going to be a summit curve. Again, two negative gradient can also form a summit curve. So in this case, what is happening? A milder negative or descending gradient meets with a steeper descending gradient. So in this case, minus n1 minus of minus n2, which is n2 minus n1, is actually going to be positive. So it is going to form a summit curve. So we know about this summit curve. Now let's look into the what type of curve we generally provide in this summit curve. So one is that ideally we should circular curve is good because the circle we know its constant radius and therefore the side distance available is going to remain constant throughout the curve section. Apart from that, the deviation angle of vertical curves are on this is going to remain almost constant along the circular curve. But whenever we are going to construct in the field, the actual deviation is quite small, and if the actual deviation is quite small, then we can easily fit a parabolic curve which is almost like a circular curve. Why we choose a parabolic curve, simple parabola particularly? Because it is easy to do the arithmetic and find out what would be the height or the elevation at certain point. As you see the equation, I mean, you know that y equal to x square type of equation. If you know the y distance or x distance, you know what is the height it's going to be. And in the next slide or so, you will be seeing that as well. Apart from that, parabola also gives a good riding comfort. Why? Again, you need to look into, you can recall the things which we talked about in the horizontal curve. What we said in the horizontal curve is that between the curve and the tangent section, we need to provide a transition curve. So the transition curve helps to provide a transition for this infinite radius to certain radius. Now, if you look into the parabola property, it is actually doing that. So at the tip of the parabola, you have a maximum radius, and whereas as you go further, the radius actually or at the tip of the parabola you have the minimum radius or the curvature is quite high. Well, if you go far off, the radius increases, it's almost going to go to tangent and going to infinity and meet with the tangent nicely. So this is why it is going to give a good ride comfort. And for all of these reasons, basically the in the summit curve we generally use the parabola. Now what we are going to use in the valley curve, we'll come to that later. Now when we consider about the design aspect of this summit curve, there are a few points we need to consider. One is the user. The users are the driver and the passenger of the vehicle. So we need to look into their comfort. So how the centrifugal acceleration is helping and how it is being introduced. So as I told you that the centrifugal acceleration is going to be introduced gradually if the radius is actually decreased from infinite to certain radius. So this parabola actually does that. And it also, you need to look into the profile, how the profile is looked into. So if you are providing a parabola, it will give you a smooth profile which is gradually changing the radius, whereas circular is not going to do that. You as a driver is going to see all of a sudden there is a change. Now the other thing is that while in the summit curve, what is going to happen, the centrifugal force on the vehicle is going to act upward, whereas we know the weight and the mass, everything is, or basically it's going to act downward due to the gravity. So passengers and driver are going to feel lighter because there is a centrifugal force which is actually will make their weight lighter, quite comfortable compared to when you are going downhill and there is a curve like a valley curve, when the centrifugal force is also acting downward as well as the weight. So you can think of a situation when you are inside a lift or elevator. So when the elevator is actually going upward, all of a sudden the change in acceleration is going to impose some additional acceleration is going to be downward, change in acceleration is going to be downward, and the weight is going to be pulled downward. So that way you will feel uncomfortable. So you will feel that your weight has increased and little bit uncomfortable. Whereas when the elevator is coming downward, it's the opposite reaction. So this is what is going to happen in the summit curve and the valley curve. So now let's look into the how we design the summit curve. So again, like in the horizontal curve, in the valley curve we can have two different situations. One is the length of the curve is more than the side distance, and again, as I told you, a curve is going to be designed either for the side distance or for the this side distance could be stopping side distance or intermediate side distance or your overtaking side distance depending on the road configuration. So one of the side distance, whichever is the governing criteria you choose, and you find out if the length of the curve is more than that, then this is how it can be estimated. As you know that the parabola equation can be well represented by y equal to ax square. So y is in this direction and x is in this direction. And how do we find the a? The a value is nothing but the exact deviation divided by 2l, which is the length of the curve. So here one thing you have to notice that in the vertical alignment, basically we measure the curve length along the horizontal distance, whereas in the horizontal alignment it was along the roadway, and this is how it has been done. So here when we say the length of the curve, it is actually this horizontal length. So now we know that we have driver eye height and the other side of is the object height. So if we have a driver eye height h in this case and object height is small h, so this is my height and this is my line of sight and this is the other side object, then only I can see the object on the other side. So we need to find out what should be this distance, which is it should meet the side distance. Now this capital H, in this case in this equation it is referred as a small h1. So h1 is nothing but a s1 square. S1 is up to this point, so it is coming from this basic equation, and h2, which is small h on this side, is nothing but a times s2 square. So s2 is from here to here. If we put back or if we now let's look into this, what is s1 and s2. So this is clearly written, s1 is root over h1 by a and s2 is equal to root over h2 by a. So the total of the s1 and s2 is going to provide me the side distance. So s1 plus s2 is, we are going to get this equation. Now this is equal to s. So if we square this parameter, then we are going to get this whole parameter, and this is going to give me 1 by a, and we already know a is equal to n by 2l. So if we know n by 2l, we can easily replace, and if we replace it, we are going to get this equation. Now our intention was to find l, which is the length of the curve. So l, we can find it out by this. Now here is the catch, we don't know the length, we are trying to find out the length, and we have assumed that the length is more than the side distance. So in this process, if we find out the obtained L is actually less than the side distance, so this process fails. So we need to look into the other process. So the other process is when the length of curve is less than the side distance. In this case, there is a portion in the which is going to be in the, then we need to formulate it. So according to the parabola property, basically if we draw a tangent here, this distance is actually half of the total distance where the parabola. So this is L by 2. Now we need to find out this one. We know the slope on this side is N1. So this is nothing but whatever the height difference H1, which is someone's eye height. So H1 by N1 will give me this horizontal distance. Likewise, on the other side, if we know the object height, which is H2 in my case, and the slope is N2, so H2 by N2 will give me this horizontal distance. My total side distance is going to be the summation of these three. So this is what has been put up here. Once we know N1 and N2, N2 is nothing but, in this particular case, this is positive and this is negative. The difference of this is going to be N1. Capital N is N1 plus N2. And if we know N1, then we can replace one value. N2 is replaced by N minus N1. This becomes my equation. Now we are trying to optimize, and the optimization we can do it by differentiating it with respect to the gradient N1. ds by dN1, if we do it, we are going to get this equation, and if we equal it to 0, then this will give me the value of the N1. So N1, we are trying to find out the optimum length. So N1 is, if we, from this equation, if we try to find out the N1, this is the equation we are, now we have to just replace this N1 in this equation, and once we replace here, the values comes like this. And when we simplify, it is quite easy. L is equal to 2s by root over 2h1 plus root over 2h2 whole square divided by n. So this equation is pretty much similar to the previous equation, some little bit of difference. So it goes on the top, and there is another factor which is 2s minus. This is what, so root 2h and this whole square, it's going to come. If you can remember one equation, the other you can easily remember. And once you know these two equation, then you can find out what is the length. So you assume one length, and if that does, after calculating it, if your assumption doesn't satisfy, you move to the other type of length, means whether the length is less. If you assume length is more, then if it is not satisfying, you go to the when length is less than the side distance, and this is how you are going to calculate. When you are doing it for the overtaking side distance, as we told you, like stopping side distance, H1 eye height is going to be 1.2 meter, object height, and you are going to estimate that. But if you are doing the same design for overtaking side distance, because you are providing overtaking, you are allowing the vehicle to overtake in your summit curve, then you need to consider the height as 1.2 meter. So driver height you have to replace object height is equal to 1.2 meter. So both heights are going to be 1.2 meter. And now how to set out the curve, summit curve? Basically you are going to look, you know the tangent part, and from there you can look into what is the angle it is going to come up. So in the survey, you just find out what should be the elevation at various intervals, and as you go, you just make sure these elevations are meeting, and you just try to smoothen it out. That is how it is laid out in the field. Our IIC actually made our life simple. How to find out this length of curve. So how did they do it? So here in the x-axis there is a deviation angle, and then there are various vehicle speed, which is in this direction, and this is the m. M is nothing but, you have to, again I'll go back to this curve. So m is nothing but the distance from the this change in gradient to the top of the curve. So this distance, if we know, then we can actually find out what is the length of the curve. Or if you want to lay out the curve, you can actually find out this way. You know the length of the curve from the drawing and the design, you know other factors, and you can find out what is m. So you know that elevation, and gradually you just fit in based on your y equal to ax square equation. This is for the stopping side distance. Similar curve is also available for the intermediate side distance and overtaking side distance. So this will make the calculations easy. Now that completes our summit. Now we'll be moving to the valley curve. As I had explained you, the summit curve and the valley curve, the difference is the algebraic difference, and if the algebraic difference is coming to be negative, then it is going to be valley curve. So we have four instances when we can get a valley curve. So a descending gradient, steeper descending gradient meets a milder descending gradient. So n2 is positive, but n1 is negative. I mean, both are negative, but if we subtract it, n2 becomes positive and n1 will remain negative. So n1 is always greater than n2 in this particular case. Definitely this will result in a negative value, which means we are going to get a valley curve. Likewise, here descending gradient meets a flat gradient. So flat means here is 0, n2 is 0, and n1 will remain negative. So this is again negative. Now a descending gradient meets a ascending gradient. So the ascending gradient is positive, which is n2. So n1 minus n2, this will remain negative, and this n1 is already negative. So overall n value is going to be negative. So it is a value. The fourth one is this: we have a ascending, milder ascending meeting a steeper ascending. So again n2 minus n1, this is the ultimate expression where n2 is value is quite high, negative value, and n1 value is lower, negative value. So together it's going to give me a negative value, which means that we are going to get a value. Now again we are going to in the valley curve we are going to consider the side distance. Now if you are considering the side distance during daytime, actually the whole curve or whole roadway section is visible. However, what is going to happen in the night? The roadway section is visible only on the headlight. So it depends on the headlight, how far the headlight can go and how far the headlight can reach, and that is the amount of highway or the section is visible to the driver. So this is why the headlight side distance is critical for valley curve, which was not for the other cases as such. So then we need to estimate the valley curve length based on the headlight side distance. And how should we do that? Before we get into that, we need to look into the comfort criteria. So there is another thing that, as I told you, when a vehicle is going downhill and when it is meeting the curve down there, the centrifugal force is acting downward, as well as the weight of the person and the vehicle is also acting downward. The summation of this total weight is actually increasing the weight of the person or the vehicle, and they will feel discomfort. So we need to consider this comfort criteria. How do we estimate the comfort criteria? We need to look into the change in centrifugal acceleration. So the change in centrifugal acceleration is this. The C is the centrifugal acceleration, and the change is going to happen. So the change at the curve at the bottom, it is going to be v square by r, where r is the radius. At the tangent, when the curve began, at that time it is 0 because r is infinite. So this is the total change, and this is happening over the time t. So this t is nothing but the distance divided by the speed of the vehicle. So if we replace this t here, then centrifugal acceleration is going to be v cube by l r. Now from this we can get L, the length of the curve, as v cube by cr. Another part, we know that we are saying r as the radius. R in this case is nothing but L by n. So L by n, you just need to understand this, we are considering the half part of the curve, not the complete part. This L by n, if we replace it in this equation, then it becomes L is equal to n v cube by c. So this is the half part. There is another half, so we need to multiply with 2. So the total, it becomes 2 times n v cube by c. So this is based on the comfort criteria. At least this length should be provided in the valley curve. Let's look into the side distance criteria, how it works. As I told you, the side distance criteria, we have to look into the headlight. So the headlight is going to go straight. So in this particular figure, if you see the red line, this is straight, and there is little bit of deviation. If you look into the projector inside the headlight, so they are at certain angle, and because of that angle, the light is deflected little bit on the upward side as well with an angle alpha. So if we know this alpha angle, and which is we generally know from the manufacturer specification, and is generally close to 1 degree or 2 degree, mainly it is 1 degree, and then we can easily find out what is the length. So the length in this case, it is going to be, if you we are trying to find out if the vehicle is here, how far it can see. So the vehicle here, it can see is the height of the eye, which is here up to this much, and the deviation of the headlight, which is S tan alpha. So this is alpha, then this is S tan alpha, and this is the distance headlight. So if this is my distance, then S tan alpha plus h1 is the total height which you can see. This is again, if you look into the parabolic equation, it is nothing but a times s square, which is my side distance. And a, as we know from the parabola equation, basically it is going to be n by 2l. So if we replace this s h1 plus s tan alpha is equal to n s square by 2l. So from this, if we just try to find out what is the length is going to be L equal to n square by 2h1 plus 2s plus tan alpha. Now one thing you have to understand here is that this 2l, whenever n by 2l we are considering it, we are considering the complete length. So 2l is the total length. So so this length is going to be L times this one. So this will give you the length of valley curve when the curve length is actually more than the stopping side distance, or just the side distance. S is the side distance. If you need overtaking side distance, you have to provide the overtaking side distance. If you need intermediate side distance, you need to provide the intermediate side distance. The things changes when the length of the valley curve is actually less than the side distance. So in this case, you have to accommodate the tangent part as well. So here this distance or this distance will remain same, whatever the height of the eye, that will remain same, and what is the angle S tan alpha, that will remain same. So the left hand side remains same, whereas the right hand side, which is you are trying to find out the horizontal distance x component, there it is going to change. So there are two components, S minus L by 2. So S is the total side distance, and L by 2 is the portion of the tangent, which is going to be here, or if you recall the summit curve, it's L by 2. So this is the portion which is going to remain in the tangent, and times n, that will give me the distance in the horizontal direction. So these together, if we try to solve this one, we'll get the length as L equal to 2s minus 2h1 plus 2s tan alpha by n. So this is again very much similar to this one. Just if you try to see the difference, you will easily recall that how this difference is coming up and what would be the this distance. So here is n s square, here in the denominator it is only n, and this parameter remains same, which was in denominator it went to numerator here, whereas the whole term is negative and it is subtracted from 2 times the stopping side distance. So this is how we calculate. Now before I move on to the next slide, I got a question. Does the position of sun affect the calculation of stopping side distance or OSD? The position of the sun does not affect, because whatever the position, you can still see the whole region. If your position of the sun is actually obstructed because of the hill and it is going to get dark and someone needs to turn on the headlight to see the road, yes, at that time it may affect, and that needs to be considered. So it's more, again it is coming back to the headlight, not the sun. As we had shown you some graphs how to estimate the these distances for summit curve, we have similar thing for the valley curve as well, and the curve is quite simple, or the similar way. you have the speed on this direction, you have the deviation angle, this is the length, and from there you can easily find out what is the um, length of the curve and what could be the speed in that particular region. So this so in this thing, another which I'm not covering or which is actually understood is that the side distance. So the side distance estimation, you have to recall on the first day's lecture when we said that how we are going to estimate the side distance for stopping, for overtaking, for intermediate. So we have to use those equations to find out the side distance and use whatever the value we are getting there, we have to use it here to find out the length of the valley curve. So that is the complete process, and if you find that it is not meeting the length, then again you have to go back to the side distance. Suppose if it is not meeting if it is not meeting due to this comfort criteria which we had discussed earlier, like for this region, then you have to revise the length, and based on the revised length you have to find out what is the revised side distance, and based on the revised side distance you have to go back and see if you really need to impose some speed limit on that particular curve. So now if I move to this summary, before I move there, there is another question. If stopping side distance is not given, how can we recognize whether length of valley curve or stop is more or less than the stopping side distance? So as I told you, the speed of the vehicle will be given, and if you know the speed of the vehicle, you can actually calculate the stopping side distance or whatever the side distance you need according to the process which we had discussed in our first day's lecture. So that needs to be calculated and then used it here. Now coming to the summary of the valley curve, basically cubic parabola is the most common thing which is preferred in the valley curve, but our IRC says the square parabola, which is like y equal to ax square, and that is why you see most of the equations are based on that. So if you are using the cubic parabola, this is how the equation is going to change: y equal to bx square, where v is equal to 2n by 3l square. So you can just replace these values at whatever the derivation we did for the square parabola, and you can see how things are changing. Now another point about the valley curve which is quite important is the lowest point. So valley curve leads to a lowest point at certain location, in particularly some of the valley curve, and this lowest point is critical because you don't want the water to get stagnant there, and the water is coming on the road. So this lowest point you have to ensure that there is enough drainage, cross drainage and longitudinal drainage, all these, particularly the cross drainage, so that the water can easily flows out of the roadway. So this is one thing. And how to find out the lowest point? This is actually done if it is unequal grade, it is, you can find it by this, the distance L times n1 by 2n into power or to the power 0.5. It is give you the distance where the lowest point is going to happen from the tangent point. If you find out, you have to just go there as a field engineer and see whether there is any cross drainage structure and how it is, whether it is adequate or not, so forth. Now before I move on to the next slide, I received another question: what would be the minimum distance of a bus stop if need to provide at a valley curve or summit? This is a very good question. The bus stop means, you mean to say the where it should be provided and how. So the bus stops are provided according, first of all, according to the convenience of the passenger, where they have crossroad and where they are going to act. Now if you are providing a bus stop, first of all you need to make sure that it is at a considerably flat terrain. At all you cannot meet the flat terrain. Whenever you are providing the bus stop, you have to see whether you have enough distance so that the bus can actually come to dead stop at the stop location. So this enough distance is going to be in the what we said, that there is a like extra lane which you are going to provide. It's a lane on the side you will be providing to the bus stop, and this lane, if you have enough distance, so the bus can actually come out of the main line and go to this deceleration lane, and in the deceleration lane basically it will slow down and come to the stop. So this is what you have to take care, and and this can be calculated based on again the stopping side distance, and so basically your deceleration lane should be at least up, and then you can take care of it. I hope I answered that one. Now the another question was that why operating side distance is not considered for calculating length of valley curve. Sorry, why overtaking side distance? So the overtaking side distance, I'm saying that overtaking, we are not going. What I tried to say here was that these equations are for side distances. So if you need to provide overtaking facility along the valley curve, definitely you need to consider overtaking side distance instead of S, which is here it is stopping side distance. You can need to provide overtaking side distance. So there is it all depends on like whether you want to provide intermediate side distance, overtaking side distance, or stopping side distance. So this is just an instance. If you are considering stopping side distance, that is how it is going to look like. So depending on that length, you are going to provide this equation. Other than that, it is going to remain same. Now I got another question. Can you tell about us how highway or designing in field of highway engineering and in terms of design? So I'm trying to understand this question. Highway of designing in field. So is this how the highway design in the field is different from the highway design what we learned so far? I'm guessing that is the question. So the answer is that in the field, when they are in the not in the field, or actually these highways are designed in the design office using various software, designing software, and some of the popular softwares are Civil 3D, MX Road, InRoads, then there are Geopack, there are X number of other softwares which can be used. And these softwares actually does all the calculations or whatever we did or whatever we learned here in the background and provide the highway. As a design engineer, we need to select the proper point of intersection where the curve is going to be there, and we need to provide the proper vertical point of intersection where the vertical curve is going to be there, and the softwares are nowadays smart enough to tell you where it is actually not meeting the design criteria, and it will show you in the red, and as a design engineer you just need to go and see why it is not meeting, and accordingly you need to change by trial and error method, changing the PI location or fitting with a different curve, or if you need a design exemption from the speed point of view, all those things you need to do. So that is how it is being done. But when someone is reviewing the design, they are recalculating it, some of the thing as a proof check, they again go back to this basic understanding, and from this basic understanding they calculate the radius, they look into the side distance, they look into other details for that. The extra widening is also again can be done by the software, but you have to tell the software that you provide the extra widening using certain formula, certain guidelines. You also have to tell the software that how many lengths you are going to provide and so forth. Now few other questions which I got, one is that for safety point of view, which curve is more feasible, valley or summit curve? So comfort point of view, as I told you, summit curve is better. Now from the safety point of view, it all depends on the speed. So if you are at a higher speed than the speed which the curve is designed, if you are on a summit curve, your vehicle can be thrown off from the road. And on the contrary, if you are at a higher speed than the speed what a valley curve is designed, so when it is negotiating the valley curve, the bottom point, your car's suspension system can bottom down and can hit the bottom of the road. So either case there is a safety issue, and it depends on how much it is, how far, I mean how higher speed you are going to go. Yes, now another thing is that if you are going to the valley curve, naturally because of the downhill gradient or descending gradient, your speed is going to keep on increasing. So if you don't check, then definitely that is where the safety the vehicle can get into accident. So this becomes more critical than the summit curve, because in the summit curve, once the vehicle is going as in the ascending gradient, naturally because of the ascending gradient, the speed is quite checked, and unless someone is actually pushing the accelerator too much, they are not going to overspeed like easily. Here in the valley curve, without even pressing the accelerator, the vehicle can. So the next question was, what will be the effect on road if the design consideration of summit curve is not suitable? So if the design consideration of summit curve is not suitable, then it means the speed is not considered properly. So as I told you, if someone is traveling at a higher speed, the vehicle can be thrown off from the summit curve. So that is the major thing which is going to happen. And the other thing is that if it is not designed properly, if particularly if it is not meeting the stopping side distance, so if there is any object lying on the other side, a stationary object, the vehicle may not be able to see and get into accident. If you have provided overtaking zone, and if it is not designed for that height, so again it can get into accident because it cannot see the oncoming vehicle. The other another question which I received is, the valley or summit curve increases the effort, then how is it beneficial? Can we alter the gradient? The valley curve is for the vehicle point of view, valley curve is not increasing the effort at the time of going downhill. It's only going after negotiating the valley curve, when it is coming out of the valley curve, and if it is ascending gradient, that's summit curve. When it is going towards the summit curve, actually the effort is increased. So once the vehicle negotiates the summit curve, then it is actually eased out. Now in both cases, basically we are doing this thing because there is a change in gradient. Now you can flatten out the gradient. What is going to happen? Your earthwork is going to increase and your construction cost is going to increase. So I'll come to those things. I mean, I have already told, and I'll come to those things like flatter gradient, what is the effect, and when we actually see the next few slides. Where another question is, which curve will be provided? So it depends on your gradient, which curve is needed there. So in the mountainous terrain, both type of curves are going to be there. Valley or another question which I received, if we will provide small trees on the median of a valley curve to prevent the glare of headlight, then no need to calculate the length of valley curve for headlight side. The headlight side distance is not for the glare from the opposite. It is the headlight. When the headlight of the vehicle which is traveling falls on the road, then only they can see the road, and then the vehicle can travel. So it is their own headlight. It's not for the other headlight. So the small trees or the bushes which you provide, the shrubs along the median, that is only helping the glare which is coming from the other side. So that is a different aspect altogether. That is not part of the this design. Now we need to look into how we can combine the two alignments, or the horizontal alignment with the vertical profile, and this is quite critical because if you want to understand the highway design, basically you have to provide both things at various locations, and when you are providing, you should actually follow certain norms. Then only the design is going to be safe and then good. And this is why the general statement is horizontal and vertical alignment should complement, and when we complement, we should actually have a proper balance between the curvature and the grade. And when the proper balance happens, we can actually avoid these two situations, like excessive curvature to achieve flat grades, which someone was asking, like if both are vertical and summit curve is so difficult, then why can't we flatten it? This is it should be avoided, because then that will introduce excessive curvature in the horizon, and excessive grades to achieve flat curvature. So this is also not advisable, like excessive grade to achieve flat curvature. So which means that you are connecting two cities and there is a hill in between. So to make your road straighter, you want to go on the top of the hill straight and again go down on the hill straight. So this is also not advisable. Or if you want to again negotiate this hilly terrain, basically you go towards, if these two cities are on the north and south, basically you go too left, too east or too much west to avoid the hill. So that is also not avoidable, advisable, because it's going to increase your. Now the other point is like sharp horizontal curve should not be introduced at or near the top of bottom of the pronounced summit or sag curve. So if you introduce this thing, many times the curve, horizontal curve, gets hidden behind the summit or the valley curve, and particularly the summit curve. And when it gets hidden, diver may not perceive that there is a curve. They will be expecting, okay, they went uphill, now they are going to go downhill, and this horizontal curve will come as a surprise to them. And also we have to understand that at the sag vertical curve, or at the summit valley curve, basically the vehicles are getting the speed of the vehicle is quite high, and all of a sudden when they're high at a speed and then they see a horizontal curve, so they need to that speed may be quite higher than the for that horizontal curve. So that will be again pose a problem or safety concern for that curve. This will actually result in a erratic motion and can get into accident. So this is the situation. And also, as I told you, the intersection or the bus bay or the truck lay-by, all these things should be provided almost should be avoided on the curb and also in the higher gradient. So it should be provided in a flatter section and as much as possible, and all or in a flatter curve. So now we'll be looking into some of the combinations and how we should be balancing out. So the balance should be done, horizontal curvature and grade should be in proper balance, as I told you. Maximum curvature with flat grade or flat curvature grade should be avoided. So that is there. Now how will we coordinate? The vertical curvature superimposed upon horizontal curvature generally results in a more pleasing appearance and reduces the number of side distance restriction. So you will see some of the images or where you will see if we do that how it is helpful. Now successive change in profile not in combination with horizontal curvature may result in series of humps visible to the driver. For how this is going to happen, some of the perspective, here are some of the images. So you have like curves like this and it is in a flat gradient. So how the perspective view is going to look like this. The next curve is not going to be visible for the driver from this when they are actually negotiating. When they don't see the road, of course they are hesitant, they don't know whether what is the curvature amount, and there will be an operation effect, means they will be slowing down, or if they are coming at a high speed they will be drastically trying to slow down and the vehicle can go off. So these are the another thing is like if there is a horizontal alignment and you don't provide a curve and the vertical end is flat, so then this will look like this thing. It's not a pleasing appearance and the driver will behave. So if you provide a curve like this, then it will look smooth and it is going to be smooth ride. So before I move on to the next, I have another question. In which type of condition we can provide valley curve? So it depends on the depends on your gradient. So as I told you, if your gradient, the difference of the gradient, algebraic difference of the gradient is positive, you are going to provide a summit curve. If your difference is negative, you are going to provide the valley curve. So I'm not sure why the sound is echoing, because we don't have any microphone here or a speaker here, so it could be somewhere else. So hopefully now you can hear better. So let's move on to the next slide. Another condition of coordination is with the environment or the area through which a highway is going. It should be you should actually see what is the scenic thing is there in the highway, and when possible, so we should actually, when possible, alignment should be enhanced scenic views of the natural man-made environment. How we can do that? Highway should lead into, not away from the outstanding view. So if you have a river like this, if you are actually constructing a highway straight line like this, which it is nice, but it is not actually meandering along the river, but if you do this one, then it is going to be quite pleasing. So that is why we are saying that highway should lead into, not away from the out. And how we should consider, it should fall towards features of interest at low elevation and rise towards feature best seen from the below or in silhouette against the sky. So things which you like to see against the sky, like the mountains and all those things, at that point if you have a gradient, upward gradient, that is quite good. And if you want to see a river which is down there in the valley, so if you put a descending gradient, that is quite good. Then the other condition which is going to come up is here. So if you have a alignment like this or the horizontal alignment like this, there is a curve and then there is a tangent section like this. So when the vehicle is here, it can actually see the this portion of the highway, the tangent, and particularly if it is a of this gradient in this portion. So they are actually sitting here, they are seeing the upward, so they are seeing it from the side, and when they are seeing it from the side, if there is a vertical curve like this, so what they are seeing is actually the bumps, and when they see the bump like this doesn't come very well to the driver. They will see it as a bumpy road. But as a design engineer, we want to create a smooth road. So what we should do here, actually we should provide try to smoothen it out by this dotted line or balancing it out, not to provide too many vertical curves like. So this is how we can coordinate. The next thing is the coordination of the PIs. So here is my horizontal alignment and here is my vertical alignment. So the PI of this horizontal alignment is here and the vertical alignment is here if it is matching, and if it is on this direction, and this is a summit curve, and this is in this direction, this is valley curve. So altogether this is going to give you a pleasing ride condition. Whereas if it gets slide little bit, and if it is not properly coordinated, if your PI, vertical PI, is shifted little bit here and this one, then it is going to be difficult for the driver as well to negotiate. As we remember that we should actually provide the curvature, horizontal curvature, right on the top, not on the other side of the vertical curve, or right before the summit curve, not on the other side. So this is what is actually we are coordinating. If we move it other side, it is going to be difficult. So you have to consider the roadway which is going from one direction to the other. So you have to consider both side traffic. So I got another question, I mean the same question, which is in which type of condition we can provide valley or summit curve. I think I have answered, saying that it depends on the condition and depends on all this perspective issue. You should consider which curve. There is no hard and fast. I'll say that you have to provide vertical curve or you have to provide summit curve, but depends on the gradient and so forth from which you can see that what curve you need to provide. So here is another condition, like if you have a horizontal profile like this tangent and a curve, and in this curve you also have a valley curve. So when someone is traveling in this tangent section, their eyesight is going to be like this, so this portion is going to be totally lost, and when they get lost, this is what they don't have any idea how the road looks like here. So it's complete box type of thing. This should be avoided. So the way the good practice of designing is that in a horizontal, in a clear view, there should not be more than 2 breaks, means 2 curves, and in the vertical there should not be more than 3 breaks or 3 curves, like here is 1 break, here is another break, here is another. If you try to follow this type of thing, the road is going to be pleasant and it's going to be nice. And again, I'm going to come back to the design aspect which we had discussed in our very first class, or shown in the very first class, how the horizontal alignment and the vertical profile is going to look like. Here is the plan where you have the alignment, the tangent part. It's going to show all the lengths and the median and the details of that. This is actually designed using some of the software, and the software in the background, it is doing all the calculations which we have learned so far. And if you don't know the calculation, if you just rely on the software, then the problem is that depending on the condition, you won't be able to change the criteria, and you won't be able to know why the software is saying that, giving you the warning and how to take care of the warning. Because if it doesn't meet certain stopping side distance or the side distances, or if there is some issue, it's going to give you the warning. And the warning, if you want to take care of it, you need to know the design. So this is the vertical profile of the horizontal alignment, the same one. So here here is one gradient, here is another gradient. So we are providing a vertical curve here, which is shown in this vertical profile, and this curve, once we provide that, basically it is a valley curve, and we look into the other factors. What is the, here it is, we are looking into the horizontal. There we can actually, whenever we are reviewing it, we can see whether there is a horizontal curve as well or not, whether it is properly coordinated or not. So here, as I told you, in the valley curve, we have to be careful whether there is any cross drainage structure, because this is the critical point. Water is going to come down from this side, and this side we need to make sure they has adequate drainage. And here you can see the cross drainage structure. So when someone is reviewing or someone is designing, needs to make sure that there is a cross drainage structure and there is sufficient provision for water to flow out. And this is the complete criteria of that. As I told you, the intersection should not be on the curve or on a flat section. So this is some condition where we are not putting the intersection right here, but before the curve. Another thing we are seeing that the intersection, wherever it is meeting, it is actually on a bit flatter terrain or flatter gradient. So this is how we ensure and make sure the design is proper. So with that, my lecture ends for today, and there will be a proctored quiz after this, and if there is any question, I'll take few questions. So the first question which I received right now is what are the various softwares for highway geodetic design? Various softwares are, there are few Bentley softwares and Autodesk software. Autodesk software is called Civil 3D. Bentley softwares are MX Road, InRoads. So in India we use MX Road. Europe also to some extent they use MX Road. In US they use InRoads. There is also another software from the Bentley and Geopack. Nowadays they are moving into the open roads type of software, which can go in any direction. Now, where this question is coming, I don't know what is negative super elevation. Negative super elevation is part of railways, not part of highways. But in highways, in some condition, we may need to provide the super elevation which is in a different direction. So it is much prominent, and it is actually much more there in the railways, because the branch out can happen on the curve, whereas in highways we have better control and we don't want the branch out to happen on the curve but on the tangent sections to avoid any negative super elevation. So the super elevation, if you need your outer edge to be raised, in case if you because of certain constraint you are not raising your outer edge but you are raising your inner edge, that is your negative super elevation. One more question I got: can we decrease speed instead of doing such horizontal or vertical alignment design? Yes, you can decrease speed, but how? At certain critical condition, you may need to decrease speed, but decreasing speed is actually not meeting the driver's expectation. Because if you are giving a highway and ask the driver, hey, I have constructed a highway, this is expressway, and you can travel at 100 kmph, and then you put a section which will require the driver to come down to 40 kmph. Is it going to meet the expectation? Because the driver, when they are on the expressway, they know that okay, I can drive at 100 kmph. So that is not the good solution, but yes, in some extreme cases you may need to do that, but it has to be done with caution and it has to be looked into. And if you look into the statistics, accident statistics or the safety statistics, most of the places where the accident happens, where the speed is reduced drastically. Another interesting question I got: if any religious place becoming obstruction in design, then alternate ways are there for alignment. This is related to the policy of a country and the process. So most of the countries in the world, they say if there is a established religion place or historic place or environmentally preserved locations, all these things needs to be avoided, and you need to have less impact when you are deciding the alignment. So this comes under that category. So and this will look into the cost benefit analysis as well. So after you consider all these things, then you can be you can look into that. Okay, so someone said that reducing speed can be economical than increasing elevation for highway. So reducing speed is economical from the construction point of view, and as I told you, alignment needs to be designed from the operation point of view, from the overall cost of point of view, user cost point of view. So reducing speed, if it leads to hundreds of accidents every year, and if you add that cost, do you think it is going to be still cheaper? You need to do the life cycle cost of that. So construction, yes, it is cheaper, but other cost is going to bump up the cost, and as far as our experience, it is actually expensive if you consider the life cycle cost. So that, one more question, whether transition curve can be provided between summit and sag curve. So transition curve, if you are providing a circular summit and sag curve, yes, you may need to provide the transition curve. But if you look into the radius of this, if you are providing a circular curve, the radius of this circular curve in summit and sag curve, these radiuses are quite large, and it can be easily bond with the tangent section. So eventually you don't need some transition curve because of the large radius. The same thing which we said for the horizontal curve, if the radius increases beyond certain point, you don't need transition curve. And most of the cases in the vertical alignment, the radiuses are so large that it is actually not needed. The other part is like if you are providing the parabolic nature, the way it is, it takes care of the transition. So that is the whole point of considering the vertical curve as the parabolic, the square parabola or cubic parabola. Another question we got, can we attend some certificate courses related to highway design at your center? So this is a center related question. QEEE members, we do if no side distance is available while designing in hilly areas. So if not, you have to provide some side distance, the minimum side distance. There is no road without no side distance. So if you are designing that, that's not a design actually. It's just you are wherever you can lay a road, that is what it is. So the whole design purpose is you have to make sure that the side distance is there. Now if you cannot meet the side distance for certain speed, as I told you, in some extreme condition, you may need to reduce the speed, you may need to look into some other alternative options. And this is, again, there is no straightforward answer what alternative option, how we are going to consider. It varies from site to site. The other one more question, do we provide super elevation on valley and summit curve? So how do we provide the super elevation? Super elevation is to provide increase the outer edge, and so that you can take care of the centrifugal force. So in summit and valley curve, if it is just pure summit and valley curve, your centrifugal is acting either upward or downward. So how we can raise the edge to do this? You can think about it. Of course, if there is a horizontal curve on this summit and valley curve, for that horizontal curve, the centrifugal force is acting outward, and for that you need to raise the outer edge, and there you can provide the super elevation. Another question, why do we provide flexible pavement for airport runway and not rigid pavement? So I'm not this question is related to the airport, and I'm teaching highway, so I defer this question whenever you are taught the highway. So the question number 4 is about the stopping side distance. So the question number 4 is about the stopping side distance, and if you recall, we had discussed about stopping side distance, how to estimate that, and in that estimation process, we need to know the acceleration due to gravity, which is g value, vehicle speed, friction factor. We also need to know the lag time. So here this reaction time or the lag time is given 2.5 seconds. Acceleration due to gravity is given, which is 9.8 meter per second square. in this particular case it's a down gradient, means expectedly your stopping side distance is going to be more, and there was a formula f plus minus n percentage. So that n percentage is given, and in this case it is descending gradient, which means your denominator should be less, which means n or descending gradient is negative, so you have to use minus n. And you have to be careful about the vehicle speed. So the formula which we discussed mostly was for meter per second. However, here it is given in kilometer per second. You have to appropriately convert it into meter per second. Question number 5, which is about designing super elevation for a horizontal curve. So we have the radius is given, design speed is given, then we have asked you to follow the IRC method. So if you recall the IRC method, you have to consider the 75% speed without ignoring the friction factor, right? So once you ignore the lateral friction factor and try to find out what is the expected super elevation, and if your expected super elevation is within 7%, you are good. If it is more than that, means you have to restrict your super elevation to 7% now, and for the full design speed or 100% design speed, you have to find out what is the expected lateral friction coefficient. So in this, if you find out the lateral friction coefficient is actually more than 0.15, you need to go to step 3. If it is less than that, you are good to go, and that is what the super elevation you are going to provide. Now in case if it is more than 0.15, what you need to do is that maximum lateral friction you can consider is 0.15, maximum super elevation you can consider is 0.07 or 7%, and when with that you have to recalculate what is the design speed this road should have. So based on that you will get a different design speed which could be less than the original design speed which you used for the design. And whatever the design speed you get there, you have to consider the speed, because in the roadway you will see the speed in the multiplication of 5. So you are not going to go on the higher 5 but the lower 5. So if it is coming 98, the design speed or the posted speed should be at least 95. If it is coming up 92, we'll be considering it as 90. Likewise. Question number 6, which is about 2-lane highways, a horizontal curve radius of 250 meter and the total pavement width of 7.5 meter at the curve. The minimum side distance of 240 meter is to be provided at the curve. Assume the length of the curve to be greater than the side distance. Determine the setback. So the question number 6 is about to find out the setback distance. So if you need to find out the setback distance, as I told you, the radius is actually the center line of the roadway. Now your if it is a 2-lane, 7.5 meter means 2-lane, is at the center, means there is 1 lane on the left side, 1 lane on the right side. Now a vehicle is going to see whenever it is traveling, it is actually middle of one of inside lane. So you have to find out the distance which is at the middle of the inner side lane, which is small d. The small d distance is going to be 7.5 meter, means which lane is going to be 3.75 meter, and 3.75 meters half is going to be your d distance. And if you recall the formula which we had, from there if you put it properly, first you need to calculate the angle which is alpha, and if you calculate the angle properly, and then if you fit into the offset distance m value, then you can get the setback distance. So now we'll move to the question number 7. So question number 7 is about grade compensation. So we talked about we need to do the grade compensation. So in this case there is a ruling gradient of 6%, and also there is a horizontal radius, which is 60 meter. Now if you recall, there is a minimum grade compensation and there is a maximum grade compensation, and also there is a gradient beyond which you don't need to do the grade compensation, which was 4%, and a minimum there are two formulas in there. If you look into those two formula, you will get the minimum and the maximum, and if you from there you need to choose whichever is there for the 6% or for the 60 meter. You'll get some grade compensation, and whatever that value, you need to deduct it from 6 and find out what will be the compensated grade. So that compensated grade you are going to provide. Now in case that grade compensated grade is less than 4%, you don't need to go beyond 4%. So the grade which you are going to provide is going to remain as 4%. So that is how it is going to. And so that you have to do the same exercise again when it if your ruling gradient becomes 5%. So that was about question number 7. Now we'll move to the question number 8. Estimate the psychological widening required for 2-lane highway with lane width 3.5 meter at a horizontal curve of radius 200 meter. Assume design. If you recall the extra widening required, there were two parts of the extra widening. One was the mechanical widening, another was the psychological widening. The psychological widening had a empirical formula through which you can find out. And the other mechanical widening, it was derived based considering the length of the axle and so forth. So here the question is about the psychological widening. So in the psychological widening, they need to find out, you need to just find out using those empirical formula what should be there, and that needs to be added to the pavement width to give you the psychological widening. Another thing about the psychological widening, if you recall, if it is more than 1 lane, then only you need the psychological widening. So here it is 2 lane, definitely you need psychological widening. So that is what is about question number 8. Now if we move to the question number 9, the question number 9 is about designing the curve length based on the comfort criteria. So this is about a valley curve where you have gradient change in the gradient, which is capital N is given 5%. You have to find out the length of the valley curve for certain design speed, which is 60 kmph, and centrifugal acceleration rate is given, which is C value is 0.6 meter per second cube. So today we derived how to get the length of a valley curve for certain centrifugal acceleration rate and the speed. So in the end of the derivation, we found out the length of the valley curve will be L equal to 2 times certain factor was there. So that is what the equation you have to use. By understanding that, you can actually solve question number 9. Now the last question, question number 10, is about finding the length of summit curve for stopping side distance of 180 meter and at a junction of a rising gradient and the falling gradient. So you have an ascending gradient of 1 in 50 and a descending gradient of 1 in 30. So from this you can find out what is the capital N value or the change in gradient, what is happening. Once you know that, then you need to find out the summit curve. So summit curve depends, there are two different formula in which you need to find. One was when summit curve is more than the side distance, another was when the summit curve is less than the side distance. You start with one assumption, either more or less, and see whether your assumption holds good or not. If not, you have to move to the other one, and definitely the other one is going to be good. So based on that, you need to find out. Now in this case, we have said it is a stopping side distance. So stopping side distance means your h1 and h2 in that formula. If you see, the height of one is going to I is going to be 1.2 meter, and whereas the height of the object is going to be 0.15 meter. So based on that, once you calculate, you will get the summit curve length. So this is all about the 10 assignments. Any question? So I already got a question. The question is, does overtaking side distance any affect by any gradient? The overtaking side distance, if you consider the gradient, yes, it does affect. Now the thing is that the effect is mutual in the way like the oncoming vehicle, whenever it is coming, if it is coming in downgrade or descending gradient, the overtaking vehicle is actually going in the ascending gradient. In that case, basically whatever the time it is taking for the ascending and the descending gradient, that there it needs to be considered. How much time it takes to that capital T, which is actually the time which it takes to overtake. So in that overtaking process, if the acceleration rate remains same, then the effect is not going to be. But the acceleration, if the acceleration rate changes based on the gradient, if we have that information, then definitely the capital T is going to change, and accordingly we have to revise the. But in general, like when you are solving the problem, mostly you won't get a different acceleration rate for the gradient. But another thing you have to consider is like the same road, the same overtaking operation can happen in the other direction. So if the overtaking is happening in the ascending gradient, the overtaking can also happen in the descending gradient. So keeping both things in mind, someone needs to consider what is the critical one, and accordingly you have to consider the overtaking side distance. Now once you know the overtaking, that's all. Thank you very much to all of you.